Deep beneath your feet, far below the foundation of your home, below the deepest mines and the furthest reaches of human exploration, lies a realm of unimaginable heat and pressure. Here, in the heart of our planet, temperatures soar to levels that rival the surface of the sun, and rocks flow like water under pressures that would crush any known material from our surface world. This is where the story of volcanoes begins, not on the mountain sides where we see their fury unleashed, but in the very core of Earth itself, where the engines of geological destruction and creation have been running since before our planet was truly a planet at all. 4.5 billion years ago, when the solar system was young and chaotic, Earth was nothing like the blue marble we know today. In those primordial days, our world was a hellscape of collision and accumulation, where countless planetesimals smashed together with such violence that their kinetic energy transformed into heat, keeping the growing planet in a molten state. Each impact added more material and more heat, creating a self-perpetuating cycle of growth and thermal energy that would lay the foundation for billions of years of volcanic activity to come. As these cosmic collisions continued, something remarkable began to happen within the growing mass of the proto-Earth. The heaviest elements, particularly iron and nickel, began their long journey toward the center of the planet, pulled by gravity through the molten rock in a process scientists call differentiation. This grand reorganization of materials released enormous amounts of energy, adding to the already tremendous heat budget of the young Earth. The sinking of these heavy metals was not a gentle process, but rather a catastrophic rain of liquid metal droplets falling through thousands of miles of molten silicate rock, generating friction and heat with every mile of descent. The formation of Earth's iron core was perhaps the single most important event in establishing the conditions necessary for volcanism as we understand it today. This metallic heart of our planet became a vast reservoir of heat, not just from its formation, but from the ongoing decay of radioactive elements trapped within the Earth during its assembly. Uranium, thorium, and potassium, distributed throughout the planet's bulk, began their slow nuclear breakdown, releasing energy that continues to this day, billions of years later. Without this internal heat engine, Earth would have long ago become a cold, dead world, geologically inactive and incapable of supporting the dynamic processes that make life possible. Above this metallic core, the mantle formed as lighter silicate minerals rose through the differentiating planet. This vast rocky layer, nearly 2,000 miles thick, became the primary source region for volcanic activity. The mantle is not the uniform static layer that early geologists once imagined, but rather a slowly churning, convecting mass of solid rock that behaves like an extremely viscous fluid over geological timescales. Heat from the core below creates vast circulation cells within the mantle, where hot rock rises, cools, and sinks in patterns that take millions of years to complete a single cycle. The earliest volcanic eruptions on Earth were unlike anything we see today. In those first hundreds of millions of years, when the planet's surface was still largely molten or only thinly crusted over, volcanism was not confined to specific mountains or vents, but was instead a planet-wide phenomenon. Imagine a world where the entire surface bubbled and seethed with volcanic activity, where lava lakes covered thousands of square miles, and where the atmosphere itself was composed largely of volcanic gases. There were no distinct volcanoes in this era, only an endless expanse of volcanic activity that would gradually begin to organize itself as the planet cooled. As Earth's surface began to solidify into the first primitive crust, volcanism took on a new character. The earliest continental crust formed through volcanic processes as lighter minerals accumulated through repeated cycles of melting and crystallization. These first land masses were not the stable continents we know today, but rather small, isolated patches of rock floating on a sea of denser oceanic crust. Volcanic activity was instrumental in growing these early continents, adding new material with each eruption and gradually building up the elevated terrains that would eventually rise above the primordial oceans. The composition of these early volcanic rocks tells us a remarkable story about the evolution of our planet. The oldest preserved volcanic rocks found in places like the Canadian Shield and Western Australia reveal that the early Earth's volcanism produced lavas much hotter than anything erupting today. These ancient lavas, called komatiites, erupted at temperatures exceeding 2,900 degrees Fahrenheit, nearly 500 degrees hotter than modern basalt lavas. Such extreme temperatures were possible because the early Earth's mantle was much hotter than it is now, still retaining much of the heat from the planet's violent formation. The gases released by these early volcanoes transformed Earth from an airless rock into a world with an atmosphere, though one that would be utterly toxic to modern life. Water vapor, carbon dioxide, sulfur dioxide, hydrogen, ammonia, and methane poured from countless volcanic vents, accumulating to form Earth's first substantial atmosphere. This primitive envelope of gases created the conditions necessary for the next crucial step in our planet's evolution as water vapor began to condense and fall as rain for the first time in Earth's history. The relationship between volcanism and water would prove to be one of the most important in shaping our planet's surface. As rain fell on the hot volcanic rocks, it created a new kind of geological interaction. Water penetrated into cracks and fissures, where it was heated by the still hot rock and returned to the surface as steam, often explosively. This process not only shaped volcanic landforms but also began the long process of chemical weathering that would break down volcanic rocks into soils and sediments. Moreover, the interaction between water and hot volcanic rocks created the conditions necessary for the formation of many important minerals and ore deposits that would, billions of years later, prove essential to human civilization. The cooling of Earth's surface created a fundamental change in how volcanism operated on our planet. As solid crust formed and thickened, magma could no longer simply seep through to the surface everywhere. Instead, it had to find or create specific pathways, zones of weakness where the molten rock could force its way upward. This led to the concentration of volcanic activity in specific locations, the first true volcanoes as we understand them today. These early volcanic centers were likely simple fissures or basic shield volcanoes, broad and gently sloped edifices built by successive flows of fluid lava. The development of plate tectonics, perhaps beginning as early as 3 billion years ago, revolutionized volcanic activity on Earth. No longer was volcanism a random or uniformly distributed phenomenon. Instead, it became organized along specific zones where plates interacted. Where oceanic plates descended beneath continental plates, water-rich sediments were carried deep into the mantle, lowering the melting point of rocks and generating the magmas that would build chains of explosive volcanoes. Where plates pulled apart, decompression of the mantle generated basaltic volcanism that would create new ocean floor and occasionally build volcanic islands. This new tectonic regime created a diversity of volcanic types unknown in Earth's earliest history. The simple basaltic volcanism of the early Earth gave way to a complex array of volcanic compositions and eruption styles. Andesitic and rhyolitic magmas, products of the melting and remelting of crustal rocks, produced explosive eruptions that could scatter ash across entire continents. The gases dissolved in these evolved magmas made them prone to violent eruptions, creating the spectacular and terrifying volcanic phenomena that would eventually enter human consciousness as both destroyers and creators. As we look back across these billions of years of Earth's history, we see that volcanoes have been constant companions to our planet's evolution. They were present at Earth's birth, helping to build the first atmosphere and filling the first oceans with water released from the planet's interior. They built the first continents and continue to add new land to this day. They have been both destroyers and creators, ending some chapters of life's history while providing the fertile soils and mineral resources that allowed others to begin. The story of Earth cannot be told without the story of volcanoes, for they are not mere features upon our planet's surface, but fundamental expressions of the dynamic forces that keep our world alive. The legacy of those early volcanic processes surrounds us today, though we rarely recognize it. Every breath we take contains oxygen that was first released by life forms that evolved in volcanic hot springs. Every piece of metal we use comes from ore deposits concentrated by volcanic processes. The fertile soils that feed billions of people owe their productivity to minerals weathered from volcanic rocks. Even the stable climate that has allowed human civilization to flourish is maintained in part by volcanic processes that regulate the amount of carbon dioxide in our atmosphere over geological timescales. We are, in a very real sense, children of volcanic Earth, our existence made possible by billions of years of fiery eruptions that transformed a molten ball of rock into the living world we call home. The mountain stands silent against the morning sky, its perfect cone shape rising thousands of feet above the surrounding landscape. To the casual observer, it appears to be nothing more than a particularly symmetrical peak, perhaps notable for its beauty, but otherwise unremarkable. Yet beneath this serene exterior lies an architecture of destruction so complex and powerful that it staggers the imagination. Within the mountain, pressures that would crush submarines like paper cups contain pools of molten rock hot enough to vaporize steel. A network of fractures and conduits connects chambers and reservoirs of magma in patterns that geologists are only beginning to understand, creating a plumbing system that extends from the surface down into the very mantle of the Earth. The heart of every volcano is its magma chamber, though this term barely captures the complexity of what truly exists beneath volcanic peaks. Rather than a single hollow cavern filled with liquid rock, as early illustrations often depicted, modern research reveals magma storage systems as intricate three-dimensional networks of partially molten zones, crystal mushes, and interconnected pockets of liquid scattered through volumes of rock that can span hundreds of cubic miles. These zones exist in a constant state of evolution, growing and shrinking, heating and cooling, mixing and differentiating in response to the endless supply of heat and material rising from below. The formation of a magma chamber begins deep in the Earth, typically at depths between 30 and 60 miles, where temperatures and pressures create conditions suitable for rock to begin melting. The process is rarely simple or complete. Most magma forms through partial melting, where only certain minerals with lower melting points liquefy, while others remain solid. This creates a sponge-like mass of solid crystals interpenetrated with pockets and channels of liquid rock. The liquid, being less dense than the surrounding solid rock, begins to rise, squeezing through minute fractures and pore spaces in a journey that may take thousands or even millions of years. As this primitive magma rises through the mantle and crust, it undergoes profound changes. The decreasing pressure allows dissolved gases to begin forming bubbles, making the magma even more buoyant. The rising molten rock also encounters different types of rock along its journey, and where it has sufficient heat, it melts and incorporates these new materials, changing its chemical composition. Country rock, as geologists call the native rock through which magma passes, can contribute elements that transform basaltic magma into andesite or even rhyolite, each with dramatically different properties and behaviors. The ascent of magma rarely proceeds directly to the surface. More commonly, the rising molten rock encounters a level where its density equals that of the surrounding rocks, or where the overlying rock is too strong to break through. Here, the magma begins to accumulate, creating what we recognize as a magma chamber. These storage regions typically form at depths between 3 and 6 miles beneath the surface, though they can be shallower or deeper depending on local conditions. The magma does not simply sit idle in these chambers but continues to evolve through a variety of processes that determine the character of future eruptions. Within the magma chamber, a slow-motion ballet of physics and chemistry unfolds. Crystals form and sink or float depending on their density relative to the liquid magma. This process, called fractional crystallization, gradually changes the composition of the remaining liquid, typically making it richer in silica and dissolved gases. Convection currents develop as hotter magma rises and cooler magma sinks, creating circulation patterns that can persist for centuries. New injections of primitive magma from below can trigger mixing events, where magmas of different compositions and temperatures blend together, often providing the trigger for eruptions. The shape and size of magma chambers vary enormously depending on the type of volcano and its geological setting. Beneath shield volcanoes like those in Hawaii, magma chambers tend to be relatively shallow and elongated, following the rift zones that channel eruptions. These chambers maintain fairly consistent compositions of basaltic magma and frequently discharge their contents in relatively gentle, effusive eruptions. The magma chambers beneath stratovolcanoes, those classic cone-shaped peaks that ring the Pacific Ocean, are typically deeper and more complex, often consisting of multiple interconnected storage zones at different depths, each potentially containing magma of different compositions. The most extreme magma chambers lurk beneath supervolcanoes, those sleeping giants capable of eruptions thousands of times larger than anything witnessed in recorded history. Beneath Yellowstone, for instance, geophysical surveys reveal a magma body that extends from depths of 3 miles to at least 28 miles, with a volume exceeding 11,000 cubic miles. Most of this volume consists of partially molten rock, with only a small percentage of actual liquid magma. But even this small fraction represents enough molten rock to bury the entire United States under 5 inches of ash. Above the magma chamber, a volcano's plumbing system continues through a network of conduits and dikes that connect the storage region to the surface. The main conduit, or volcanic pipe, is rarely a simple vertical tube. Instead, it typically consists of a complex pathway that may branch, merge, and change direction multiple times along its route. These conduits form through a combination of processes, including the forceful injection of magma that cracks open new pathways, the melting of surrounding rock, and the gradual erosion of conduit walls by flowing magma during eruptions. The walls of volcanic conduits tell stories of countless eruptions, recorded in layers of different rock types plastered against their sides. Each eruption leaves its mark, whether in the form of solidified lava that lines the conduit walls or in zones of fractured and altered rock created by the intense heat and corrosive volcanic gases. Over time, these conduits can become clogged with solidified magma, forcing future eruptions to find new pathways to the surface or to build sufficient pressure to blast through the obstruction in particularly violent eruptions. The type of volcano that develops at the surface depends largely on the composition of its magma and the style of its eruptions. Shield volcanoes, built by countless flows of fluid basaltic lava, create broad, gently sloped edifices that can cover thousands of square miles. Mauna Loa in Hawaii, the world's largest active volcano, rises over 30,000 feet from its base on the ocean floor, making it taller than Mount Everest when measured from bottom to top. Its gentle slopes, rarely exceeding 5 degrees, give little hint of the vast size of the structure, which contains enough rock to bury the entire state of California under a layer 50 feet thick. Stratovolcanoes present the classic volcanic profile, with steep slopes rising to a perfect cone topped by a summit crater. These volcanoes, also called composite volcanoes, earn their name from their construction through alternating layers of lava flows and pyroclastic deposits. Mount Fuji, Mount Rainier, and Mount Vesuvius all belong to this category. Their steep slopes, often exceeding 30 degrees near the summit, result from the higher viscosity of their andesitic and dacitic lavas, which cannot flow far before solidifying. These volcanoes grow through a combination of summit eruptions that add material to their tops and flank eruptions that break out through their sides, gradually building the characteristic cone shape over hundreds of thousands of years. Cinder cones represent the simplest type of volcano, formed by the accumulation of volcanic fragments called cinders, or scoria, around a single vent. These fragments, ranging in size from ash to blocks several feet across, are ejected into the air during eruptions and fall back around the vent, building a cone with slopes at the angle of repose, typically between 30 and 40 degrees. Most cinder cones form in a single eruptive episode, lasting weeks to years, and rarely grow taller than 1,000 feet. Paracutin in Mexico, which erupted from a cornfield in 1943 and built a cone nearly 1,400 feet tall over 9 years, provides the best documented example of cinder cone formation. The global distribution of volcanoes follows patterns that remained mysterious until the development of plate tectonic theory in the 1960s. The Ring of Fire, that great circle of volcanoes surrounding the Pacific Ocean, marks the boundaries where oceanic plates descend beneath continental plates in zones called subduction zones. Here, the descending oceanic crust carries water-rich sediments deep into the mantle, where the water lowers the melting point of the overlying mantle rock, generating the magmas that feed explosive volcanoes. This process has created the volcanic chains that extend from Chile through Central America and Mexico, up through the Cascades of the western United States, across to Alaska, down through Japan and the Philippines, and through Indonesia to New Zealand. Mid-ocean ridges represent another major category of volcanic activity, though most of it occurs hidden beneath miles of seawater. These underwater mountain ranges, extending for over 40,000 miles across the ocean floors, mark zones where tectonic plates pull apart, and new oceanic crust forms through volcanic activity. Iceland sits atop the mid-Atlantic ridge, providing a rare opportunity to observe mid-ocean ridge volcanism above sea level. The island itself exists only because of the coincidence of the ridge with a hotspot, an anomalously hot region of the mantle that produces excess volcanism. Hotspots create some of Earth's most spectacular volcanic features, operating independently of plate boundaries. These regions of anomalously hot mantle generate volcanic activity that persists for millions of years as tectonic plates move across them. The Hawaiian Islands provide the classic example, with the Big Island currently sitting above the hotspot, while older islands to the northwest show progressively greater ages, recording the Pacific Plate's movement over the stationary hotspot during the past 70 million years. The Yellowstone hotspot has traced a similar path across the North American continent, leaving a trail of ancient volcanic fields across Idaho's Snake River Plain. Continental rift zones represent areas where continents begin to tear apart, creating another setting for volcanic activity. The East African rift system, extending from Ethiopia to Mozambique, showcases this process in action. Here, the African continent slowly splits apart, with volcanic activity marking the zones of separation. The unusual chemistry of rift volcanoes, including the only active volcano that erupts carbonatite lava at Oldoinyo Lengai in Tanzania, reflects the unique conditions where continental crust stretches and breaks. The architecture of volcanic systems extends beyond individual volcanoes to encompass entire volcanic fields and provinces. Monogenetic volcanic fields consist of hundreds or thousands of individual vents, each typically active for only a single eruptive episode. The San Francisco volcanic field in Arizona contains over 600 vents spread across nearly 2,000 square miles, recording nearly 6 million years of sporadic volcanic activity. Large igneous provinces represent the most extreme expression of volcanic architecture, where massive outpourings of lava cover areas exceeding 40,000 square miles. The Deccan Traps of India and the Siberian Traps of Russia preserve evidence of these catastrophic events that likely contributed to mass extinctions. Understanding the architecture of volcanoes requires a combination of techniques that allow scientists to peer deep beneath the surface. Seismic waves from earthquakes and artificial sources reveal the three-dimensional structure of magma chambers and conduits, as these waves travel at different speeds through solid rock and partial melt. Precise GPS measurements detect the subtle swelling and deflation of volcanoes as magma moves within them. Measurements of gravity and magnetic fields map variations in rock density and composition that indicate the presence of magma bodies. Gas emissions provide windows into the deep processes occurring within magma chambers, as different gases escape at different rates, depending on depth and temperature. The architecture of a volcano is never static, but constantly evolves throughout its lifetime. Magma chambers grow through repeated injections of new melt, shrink through eruptions and crystallization, and shift position as the volcano matures. Conduits become established, clog with solidified magma, and blast open again. The volcanic edifice itself grows through eruptions, collapses in massive landslides, and rebuilds. Some volcanoes maintain relatively steady activity for millions of years, while others experience long periods of dormancy punctuated by catastrophic eruptions. This dynamic architecture makes every volcano unique, with its own personality shaped by the interplay of deep earth processes and local geological conditions. The rock begins its transformation miles beneath the surface, in regions where temperature and pressure conspire to break the bonds that hold minerals in their solid, crystalline forms. What starts as solid stone, compressed and heated beyond comprehension, slowly yields to forces that have operated since Earth's beginning. Atoms vibrate faster, crystal lattices weaken, and gradually, imperceptibly, the first droplets of liquid appear between mineral grains like morning dew. This is the birth of magma, a substance that seems to defy nature's ordinary rules, existing as liquid rock in a world where rock should be solid, carrying within it the power to reshape landscapes and alter the course of civilizations. Magma is far more than simply melted rock, just as cake batter is more than melted cake. It represents a complex mixture of liquid, silicate melt, solid crystals, dissolved gases, and sometimes even chunks of unmelted rock caught up in the molten mass. The proportions of these components vary dramatically between different magmas and even within the same magma body over time. Understanding magma requires thinking beyond our everyday experience with liquids, entering a realm where materials behave in ways that seem almost alien to our surface world experience. The chemistry of magma begins with silicon and oxygen, two elements that together make up nearly 75% of Earth's crust. These elements combine to form silicate tetrahedra, pyramid-shaped molecules with a silicon atom at the center, surrounded by 4 oxygen atoms. These tetrahedra link together in chains, sheets, and three-dimensional frameworks to create the diverse array of silicate minerals that compose most volcanic rocks. In magma, these structures partially break down, creating a liquid dominated by various arrangements of silicate chains and clusters that give the melt its distinctive properties. The silica content of magma, typically ranging from about 45% in basalt to over 70% in rhyolite, fundamentally controls how the magma behaves. Low silica basaltic magmas flow almost like water when erupted at their typical temperatures around 2000 degrees Fahrenheit. The silicate structures in these magmas remain relatively simple and disconnected, allowing the liquid to flow freely. High silica rhyolitic magmas, even when heated to similar temperatures, flow like cold honey or thick tar. Their silicate structures form complex, interconnected networks that resist flow, creating viscosities 10,000 to 1 million times greater than their basaltic cousins. Temperature profoundly affects magma behavior, though not always in ways we might expect. A temperature difference of just 100 degrees can transform magma from a freely flowing liquid to an immobile solid. As magma cools, crystals begin to form, starting with minerals that have the highest melting points. Olivine and pyroxene typically crystallize first in basaltic magmas, followed by plagioclase feldspar, and finally, if the magma cools sufficiently, quartz and potassium feldspar. Each crystal that forms removes certain elements from the remaining liquid, changing its composition and properties in a process that can transform basaltic magma into andesite or even rhyolite through progressive crystallization. The presence of crystals fundamentally changes how magma flows. A magma with less than 30% crystals behaves essentially as a liquid, though one increasingly thickened by its solid cargo. Between 30 and 60% crystals, the magma enters a transitional zone where it behaves sometimes like a liquid and sometimes like a solid, depending on how fast it is forced to move. Above 60% crystals, the magma becomes a crystal mush that can barely flow at all, more like wet concrete than liquid rock. Many magma chambers spend most of their existence in this crystalline mush state, mobilizing into eruptible liquid only when new injections of hot magma remelt the crystals, or when gas bubbles reduce the effective crystal content. Dissolved gases transform magma from a mere geological curiosity into one of nature's most powerful forces. Water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, and other gases dissolve in magma under the enormous pressures found at depth, much as carbon dioxide dissolves in champagne. A basaltic magma at depth might contain only 1 or 2% dissolved water by weight, while a rhyolitic magma could hold 6% or more. These percentages seem small until we consider that during an eruption, these dissolved gases expand to volumes hundreds or thousands of times larger than the magma that contained them. As magma rises toward the surface and pressure decreases, dissolved gases begin to form bubbles in a process called vesiculation. The physics of bubble formation in magma follows the same principles as opening a shaken soda bottle, but with dramatically more violent results. The first bubbles typically form around tiny crystals or other irregularities in the magma, growing as more gas diffuses into them from the surrounding liquid. In fluid basaltic magma, these bubbles can rise and coalesce, often escaping gently at the surface. In viscous, rhyolitic magma, bubbles cannot easily move through the thick liquid, and instead grow in place until they occupy most of the magma's volume. The expansion of gas bubbles provides the driving force for explosive eruptions. As bubbles grow, they reduce the density of the magma, increasing its buoyancy and accelerating its rise. This creates a runaway process where decreasing pressure causes more gas to come out of solution, forming more bubbles, further decreasing density and accelerating ascent. When the volume of bubbles exceeds about 75% of the total volume, the magma fragments into a spray of liquid droplets surrounded by expanding gas, transforming from a bubbly liquid into a gas jet carrying particles of molten rock. Once magma reaches the surface and loses its dissolved gases, we call it lava, though the distinction involves more than just a change in name. Lava behavior depends primarily on its composition and temperature, with different types creating dramatically different volcanic features. Basaltic lava flows come in two main varieties that Hawaiian volcanologists named Pahoho and AA, words that have been adopted worldwide. Pahoho lava creates smooth, ropey surfaces that form as the surface crust wrinkles while still plastic. These flows advance through a process of inflation, where liquid lava injected beneath a solidified crust causes the flow to swell like a slowly inflating balloon. AA lava presents a completely different character, with a surface of jagged, clinker-like blocks that make walking across it treacherous, even after it cools. The transition from Pahoho to AA can occur in a single flow as it cools and loses gas, or as it encounters steeper slopes that increase flow rates. The rough surface of AA forms as the cooled crust breaks apart during flow, with blocks tumbling down the flow front like a slow-motion avalanche of red-hot rocks. Despite their different appearances, Peihoho and AA can have identical chemical compositions, demonstrating how physical conditions during flow dramatically affect the final form of volcanic rocks. The most fluid lavas on Earth today erupt from certain hotspot volcanoes, particularly in Hawaii. These lavas can have viscosities approaching that of motor oil when first erupted, allowing them to flow at speeds exceeding 30 miles per hour on steep slopes. Such fluid lavas create spectacular fire fountains that can reach heights exceeding 1,000 feet as dissolved gases expand rapidly through the low viscosity liquid. The droplets of lava thrown out by these fountains often remain molten long enough to coalesce when they land, feeding rootless lava flows that seem to emerge from nowhere. At the opposite extreme, rhyolitic and dacitic lavas emerge from volcanic vents as massive, slow-moving domes or thick flows that advance mere feet per day. These lavas are so viscous that they pile up around volcanic vents rather than flowing away, building steep-sided lava domes that can grow hundreds of feet high. The surfaces of these domes crack and crumble as they grow, creating unstable piles of hot rock that periodically collapse in dangerous avalanches. The Soufriere Hills volcano on Montserrat has been building and destroying such domes since 1995, repeatedly threatening communities with pyroclastic flows generated by dome collapses. Pyroclastic flows represent one of the most devastating volcanic phenomena, racing down volcanic slopes at speeds that can exceed 400 miles per hour, with temperatures hot enough to instantly incinerate anything in their path. These flows consist of hot gas mixed with volcanic particles ranging from fine ash to blocks the size of houses, behaving as a dense, ground-hugging current that follows topography while maintaining enough momentum to climb hills hundreds of feet high. The physics of pyroclastic flows combines elements of fluid dynamics, granular flow, and gas dynamics in ways that scientists are still working to fully understand. The particles carried in pyroclastic flows tell stories about the violence of their formation. Pumice, those foam-like rocks that float on water, preserve the frozen remains of bubbles that comprised most of the magma's volume at the moment of eruption. Volcanic ash, despite its name, contains no burned material, but consists instead of tiny fragments of volcanic glass, crystals, and pulverized rock, created when expanding gases blast magma into microscopic pieces. Volcanic bombs, large blobs of magma thrown from vents, often develop aerodynamic shapes as they spin through the air, their surfaces cooling into distinctive bread crust textures as gases continue to expand their still molten interiors. The interaction between magma and external water creates some of the most violent volcanic phenomena. When seawater, groundwater, or surface water encounters magma, it flashes instantly to steam, expanding to volumes over 1,000 times larger than the original liquid. These phreatomagmatic eruptions, as volcanologists call them, fragment magma even more finely than purely magmatic eruptions, creating distinctive deposits of extremely fine-grained ash. The eruption of Krakatoa in 1883 derived much of its explosive power from seawater entering the magma chamber, generating explosions heard 3,000 miles away. Submarine eruptions reveal another facet of how lava behaves under unusual conditions. When lava erupts beneath deep ocean water, the pressure prevents dissolved gases from expanding dramatically, suppressing explosive activity that would occur at the surface. The rapid cooling by seawater creates distinctive pillow lavas, bulbous masses with glassy rinds that form as blobs of lava squeeze out through cracks in the cooling crust. These pillows stack upon each other like a pile of giant water balloons, building volcanic structures that differ fundamentally from their above-water counterparts. The gases released by volcanic activity extend their influence far beyond the immediate vicinity of eruptions. Sulfur dioxide ejected into the stratosphere converts to sulfuric acid aerosols that can circle the globe, reflecting sunlight and cooling Earth's climate for years after major eruptions. Carbon dioxide, being heavier than air, can accumulate in low-lying areas near volcanoes, creating invisible pools of unbreathable gas that have killed thousands throughout history. Lake Nyos in Cameroon, situated in a volcanic crater, catastrophically released dissolved carbon dioxide in 1986, asphyxiating over 1,700 people in nearby valleys. Volcanic gases provide crucial information about magma processes occurring far beneath the surface. The ratios of different gases change as magma rises, crystallizes, and degasses, creating chemical signatures that reveal the state of the volcanic system. Increases in sulfur dioxide emissions often precede eruptions as new magma rises from depth. Changes in the ratio of carbon dioxide to sulfur dioxide can indicate whether magma is stalling at depth or ascending toward the surface. Modern monitoring equipment can detect these changes in real time, providing critical warning of impending eruptions. The minerals that crystallize from cooling magma create a vast array of volcanic rocks, each telling its own story about the conditions of its formation. Obsidian, volcanic glass, formed when lava cools too quickly for crystals to grow, preserves the random atomic structure of the liquid magma. Granite, which forms when magma cools slowly miles beneath the surface, contains large crystals that grew over thousands of years. Porphyry, with large crystals embedded in a fine-grained matrix, records two stages of cooling, first slowly at depth, where large crystals grew, then rapidly at the surface where the remaining liquid froze into microscopic crystals. The diversity of volcanic materials extends to exotic compositions rarely seen at Earth's surface. Carbonatite lavas erupting at only one active volcano in Tanzania consist primarily of carbonate minerals rather than silicates, flowing at the remarkably low temperature of around 1,000 degrees Fahrenheit. Komatiites, found only in rocks billions of years old, erupted at temperatures exceeding 2,900 degrees Fahrenheit from an ancient Earth whose interior was much hotter than today. These unusual lavas remind us that our current understanding of volcanism represents only a snapshot of processes that have varied throughout Earth's long history. The study of volcanic materials continues to reveal new secrets about how Earth's interior works. Tiny melt inclusions, droplets of magma trapped inside growing crystals, preserve samples of magma from various depths and stages of evolution. These microscopic time capsules allow scientists to reconstruct the complete history of a magma from its formation in the mantle through its eruption at the surface. Isotope ratios in volcanic rocks reveal the sources of magmas, whether from primitive mantle untouched since Earth's formation or from crustal rocks recycled through subduction zones. The transformation of solid rock to flowing magma and back to solid rock represents one of Earth's fundamental cycles, one that has operated for billions of years and will continue long after humanity has passed from the scene. Each lava flow, ash fall, and pyroclastic surge adds new material to Earth's surface, gradually building the landscapes we inhabit. The rivers of liquid stone that flow from Earth's interior carry not just molten rock, but also the heat, gases, and chemical elements necessary for maintaining our planet as a living world rather than a cold, dead sphere. In understanding these rivers of fire, we glimpse the deep processes that make Earth unique among the known worlds of our solar system. 252 million years ago, in what would become Siberia, the Earth began to bleed fire on a scale that defies human comprehension. The eruptions started perhaps slowly, with fissures opening across a landscape that no human eyes would ever see, releasing floods of lava that spread like burning seas across millions of square miles. This was not a single volcano, but an entire region transforming into a volcanic hellscape, that would persist for nearly 1 million years. The Siberian traps, as geologists would eventually name these vast lava fields, released enough molten rock to bury the entire United States under half a mile of lava, fundamentally altering Earth's climate and triggering the most severe mass extinction in our planet's history. The scale of devastation from the Siberian traps eruptions exceeded anything in human experience or imagination. As lava poured from countless fissures, it released gases in quantities that transformed the entire atmosphere. Carbon dioxide levels soared to concentrations that turned Earth into a greenhouse, unlike anything seen before or since. Sulfur compounds created acid rain that poisoned the oceans and dissolved the shells of marine organisms. The heating of coal deposits by the advancing lava added toxic metals and more greenhouse gases to an already poisoned atmosphere. Ocean temperatures rose by as much as 18 degrees Fahrenheit, turning vast areas of the sea into oxygen-depleted dead zones. Life on Earth nearly ended during this period known as the Permian-Triassic extinction, or the Great Dying. 96% of marine species vanished forever from the fossil record. On land, 70% of vertebrate species disappeared, along with the vast forests of seed ferns and conifers that had covered the continents. Insects, normally resilient to extinction events, suffered their only major mass extinction. The complex ecosystems that had developed over hundreds of millions of years collapsed within perhaps just 60,000 years, a geological instant that reset the trajectory of life on Earth. The evidence for this catastrophe lies preserved in rocks around the world, telling a consistent story of sudden, overwhelming disaster. In China, detailed fossil beds show thriving communities of marine life suddenly replaced by bacterial mats and sparse populations of disaster species. In Antarctica, coal deposits formed from lush forests abruptly give way to barren sandstones. Everywhere the boundary is marked by a shift in carbon isotopes that speaks to the massive injection of volcanic gases into the atmosphere. The very chemistry of the oceans changed, becoming more acidic and depleted in oxygen, creating conditions hostile to most forms of life that had evolved in more stable times. Yet the Siberian traps were not unique in Earth's history, merely the most devastating example we have identified. Throughout our planet's long existence, massive volcanic episodes have repeatedly altered the course of evolution and climate. These large igneous provinces, as geologists term them, appear to coincide with many of Earth's mass extinctions, suggesting that volcanism has been one of the primary reset buttons for life on our planet. Each event writes its story in layers of basalt that can be traced across entire continents, monuments to periods when Earth's interior convulsed and reshaped the surface world. 66 million years ago, as dinosaurs reached the peak of their diversity and dominance, another massive volcanic episode began in what would become Western India. The Deccan Traps eruptions created a volcanic province covering 200,000 square miles with layers of basalt over a mile thick in places. The timing of these eruptions has sparked one of the greatest debates in paleontology, as they coincided closely with the asteroid impact that created the Chicxulub crater in Mexico. Did the volcanic gases and climate disruption from the Deccan Traps weaken ecosystems before the impact delivered the final blow? Or did the impact itself trigger enhanced volcanism on the opposite side of the planet? The Deccan Traps eruptions unfolded in distinct pulses over approximately 800,000 years, with the most intense phase occurring remarkably close to the time of the asteroid impact. Each pulse released enormous quantities of gases that would have caused rapid climate swings. Sulfur dioxide would have created short-term cooling as it formed reflective aerosols in the atmosphere, followed by longer-term warming as carbon dioxide accumulated. Mercury, released from the volcanic vents, spread globally and can still be detected in sediments from this period, providing a chemical fingerprint of the eruption's reach. The lava flows from the Deccan Traps created a landscape of extraordinary desolation. Individual flows extended for hundreds of miles, filling valleys and burying hills beneath hundreds of feet of molten rock. The Western Ghats mountain range of modern India consists largely of these ancient lava flows, eroded into spectacular stepped hillsides that preserve the record of successive eruptions. Between eruptions, brief periods of quiescence allowed soils to form and life to temporarily recolonize the devastated landscape, only to be buried by the next pulse of volcanic activity. Moving deeper into Earth's past, we encounter volcanic events that dwarf even these massive eruptions. The supervolcano beneath Yellowstone National Park has erupted cataclysmically at least 3 times in the past 2 million years, with the most recent eruption occurring 640,000 years ago. This eruption ejected 240 cubic miles of material, covering much of North America in ash and creating the 43 by 28 mile caldera that forms the heart of the modern park. The scale of this eruption exceeded the famous Mount St. Helens eruption of 1980 by a factor of 2,500. The Yellowstone supervolcano operates on timescales that make human history seem fleeting. Its eruptions follow no regular schedule, with intervals between major events ranging from 600,000 to 800,000 years. Beneath the park today, a vast magma chamber continues to accumulate molten rock, fed by a deep mantle plume that has been active for at least 16 million years. As the North American continent drifted southwest over this stationary hotspot, it left a trail of ancient calderas across the Snake River plain of Idaho, each marking a past catastrophic eruption. The global effects of a Yellowstone supereruption would transform the modern world. Ash would blanket the central United States under several feet of debris, collapsing roofs, destroying agriculture, and clogging machinery. The injection of sulfur compounds into the stratosphere would create a volcanic winter lasting years, with global temperatures dropping by as much as 10 degrees Fahrenheit. Agriculture would fail across much of the planet as growing seasons shortened or disappeared entirely. Modern civilization, dependent on complex supply chains and just-in-time delivery systems, would face challenges unlike anything in recorded history. Yet Yellowstone's eruptions pale in comparison to the Toba supereruption that occurred 74,000 years ago on the island of Sumatra. This eruption, the largest known volcanic event of the past 2 million years, ejected 700 cubic miles of material, nearly 3 times the volume of Yellowstone's largest eruption. The Toba eruption occurred at a critical moment in human evolution, when our species consisted of small populations scattered across Africa and had just begun to expand into Eurasia. Genetic evidence suggests that human populations crashed during this period, creating a bottleneck that reduced our species to perhaps just a few thousand individuals. The Toba eruption left its signature across much of Asia in the form of a distinctive ash layer that can be traced from the Arabian Sea to the South China Sea. In India, the ash fell up to 20 feet thick in some locations, burying entire landscapes and preserving them like volcanic time capsules. Archaeological sites below and above the ash layer show dramatic changes in tool technologies and possibly even species of human ancestors, suggesting that the eruption may have accelerated cultural and evolutionary changes in our ancestors. The climatic impact of Toba likely exceeded anything humans have experienced in recorded history. Computer models suggest global cooling of 5 to 15 degrees Fahrenheit, with regional cooling possibly exceeding 25 degrees in some areas. This volcanic winter would have lasted 6 to 10 years, followed by a 1,000-year cold period as Earth's climate slowly recovered. Tropical forests retreated to small refuges while grasslands and deserts expanded. For human populations dependent on hunting and gathering, the rapid environmental changes would have posed extreme challenges, forcing migrations, innovations, and adaptations that shaped our species' development. Even further back in time, around 2 billion years ago, volcanic eruptions fundamentally transformed Earth's atmosphere in ways that made complex life possible. The emergence of photosynthetic bacteria had begun producing oxygen, but this reactive gas was quickly consumed by chemical reactions with iron and other elements. Massive volcanic eruptions during this period released enormous quantities of rocks that could react with oxygen, but eventually the rate of oxygen production exceeded the rate at which volcanic rocks could consume it. This allowed oxygen to accumulate in the atmosphere for the first time, creating the conditions necessary for the evolution of complex oxygen-breathing organisms. The volcanic events of the Proterozoic era, spanning from 2.5 billion to 540 million years ago, repeatedly transformed Earth's climate in ways that seem almost unimaginable today. During several periods, volcanic activity may have contributed to global glaciation so severe that ice covered the entire planet from poles to equator, creating what scientists call snowball Earth events. The volcanic carbon dioxide that continued to leak through ice-covered volcanic vents eventually accumulated to levels that triggered rapid warming, melting the global ice sheets in catastrophic floods that reshaped continents and created new evolutionary opportunities. The relationship between volcanism and climate operates through multiple complex mechanisms that scientists are still working to understand fully. Volcanic sulfur dioxide creates short-term cooling by forming reflective aerosols, while carbon dioxide causes long-term warming. The height to which volcanic gases rise determines their global impact, with stratospheric injections having effects that last years, while tropospheric emissions wash out in weeks. The latitude of eruptions matters too, with tropical eruptions affecting both hemispheres, while high-latitude eruptions primarily influence only one hemisphere. Throughout Earth's history, flood basalt eruptions have coincided with most major mass extinctions, suggesting a causal relationship that goes beyond mere correlation. The end Triassic extinction 200 million years ago corresponded with the eruptions that created the Central Atlantic magmatic province. The early Jurassic extinction coincided with the Karoo-Ferrar eruptions. The end Cretaceous extinction involved both the Chicxulub impact and the Deccan traps. Each event reshaped the course of evolution, eliminating dominant groups and creating opportunities for previously marginal organisms to diversify and thrive. The preservation of these ancient volcanic events in the geological record provides crucial insights into how Earth systems respond to massive perturbations. Fossil soils between lava flows reveal how quickly life recolonized devastated landscapes. Chemical signatures in ocean sediments show how marine ecosystems collapsed and recovered. The distribution of ash layers maps the extent of atmospheric circulation patterns millions of years ago. Each piece of evidence adds to our understanding of how volcanic catastrophes unfold and how life responds to extreme environmental changes. Modern humans have never experienced a volcanic event approaching the scale of these ancient catastrophes. The largest eruption in recorded history, Tambora, in 1815, ejected about 38 cubic miles of material, causing the year without a summer, but representing less than 1% of a Yellowstone-scale supereruption. Our species evolved during a period of relatively modest volcanic activity, and our civilizations developed during an even quieter period. We have built our cities, agriculture, and global systems during a brief intermission in Earth's volcanic symphony. The legacy of ancient eruptions extends beyond their immediate destructive effects. The fertile soils that support much of Earth's agriculture developed from the weathering of volcanic rocks. The ore deposits that provide metals essential to modern technology concentrated through volcanic processes. Even Earth's water may have been delivered partly through volcanic outgassing over billions of years. The same forces that repeatedly devastated life on Earth also created the conditions that allowed it to flourish in new forms. Understanding these ancient volcanic catastrophes provides essential context for evaluating modern volcanic hazards. The supervolcanoes that devastated past worlds still lurk beneath our feet, their magma chambers slowly recharging for future eruptions. The rifts and subduction zones that generated past flood basalts remain active, capable of producing future large igneous provinces given sufficient time. While the probability of such events in any human lifetime remains vanishingly small, their eventual occurrence is virtually certain on geological timescales. The study of ancient eruptions also offers insights relevant to modern concerns about climate change and ecosystem resilience. The rate at which volcanic gases transformed past climates provides natural experiments in how Earth's systems respond to rapid changes in atmospheric composition. The recovery of life from past volcanic catastrophes demonstrates both the resilience and vulnerability of ecosystems. The selective pressures imposed by volcanic disasters drove evolutionary innovations that shaped the development of life on Earth. In understanding how past worlds ended and new ones began, we gain perspective on our own moment in Earth's long volcanic history. The first humans to witness a volcanic eruption must have thought the world was ending. Imagine the terror of seeing a mountain split open with a roar that shook the earth, spewing forth rivers of liquid fire and turning day into night with clouds of ash. Yet these same terrifying mountains provided gifts that would prove essential to human survival and development. The rich soils weathered from volcanic ash, the sharp obsidian blades formed from cooling lava, the natural hot springs that offered warmth and healing, all drew our ancestors to settle in the shadows of volcanoes despite their obvious dangers. Archaeological evidence reveals that humans have lived near volcanoes for hundreds of thousands of years. In the East African Rift Valley, where our species first evolved, ancient human footprints preserved in volcanic ash at Litoli in Tanzania date back 3.7 million years. These footprints, left by our Australopithecine ancestors, were preserved when they walked across fresh ash from the nearby volcano Sadiman, their tracks captured forever when rain cemented the ash into rock. The volcanic activity of the Rift Valley, while periodically destructive, created the diverse environments and concentrated resources that may have driven human evolution itself. The relationship between volcanoes and human development extends far beyond mere proximity. Obsidian, volcanic glass formed when lava cools rapidly, became one of humanity's first traded commodities. This naturally sharp material, capable of producing edges finer than modern surgical steel, was prized for toolmaking throughout prehistory. Obsidian from specific volcanoes can be chemically fingerprinted, allowing archaeologists to trace ancient trade routes that stretched for thousands of miles. Obsidian from Lipari in Italy reached sites throughout the Mediterranean, while volcanic glass from Anatolian volcanoes spread across the Near East, creating some of humanity's first long-distance exchange networks. The fertile soils produced by weathering volcanic ash attracted agricultural settlements from the very beginning of farming. Volcanic soils are rich in essential nutrients like phosphorus, potassium, and calcium, released as volcanic glass and minerals break down. These soils also possess excellent water retention properties while maintaining good drainage, creating ideal conditions for agriculture. It is no coincidence that many of humanity's earliest agricultural centers developed in volcanic regions, from the highlands of Ethiopia, where coffee was first cultivated, to the volcanic soils of Anatolia, where wheat agriculture began. In ancient Mesopotamia, though far from active volcanoes, volcanic materials played crucial roles in early civilization. Pumice, transported down rivers from distant eruptions, was used as an abrasive for working stone and metal. Volcanic ash, traded from Anatolia, was mixed with lime to create some of the world's first hydraulic cements, capable of hardening underwater and enabling the construction of harbors and aqueducts. The Sumerians and Babylonians knew of volcanoes through trade and travel, incorporating them into myths about gods who controlled underground fires and mountains that connected Earth to the underworld. The Minoan civilization on Crete flourished for centuries in one of the most volcanically active regions on Earth. Around 1600 BCE, the volcano on the nearby island of Thera modern Santorini, produced one of the largest eruptions in recorded human history. The eruption ejected approximately 14 cubic miles of material, creating a caldera that caused the center of the island to collapse into the sea. Tsunamis generated by this collapse swept across the eastern Mediterranean, reaching heights of perhaps 30 feet on the north coast of Crete, devastating the Minoan fleet and coastal settlements. The Thera eruption did not immediately destroy Minoan civilization as once believed, but it marked the beginning of their decline. Ash from the eruption, while initially destructive, created exceptionally fertile soils that supported dense populations in subsequent centuries. The memory of this catastrophic event may have inspired Plato's tale of Atlantis, an advanced island civilization that disappeared beneath the waves in a single day and night. Whether or not this connection is real, the story demonstrates how volcanic catastrophes entered human mythology and philosophical thought, becoming metaphors for the fragility of human achievement. Ancient Egypt, though lacking volcanoes within its borders, felt the effects of distant eruptions through climate disruption and traded extensively in volcanic materials. Pumice from the Aegean was used to smooth papyrus and in cosmetics. More significantly, major volcanic eruptions elsewhere in the world occasionally caused the failure of the Nile floods upon which Egyptian agriculture depended. Tree ring data and historical records suggest that several periods of political instability in Egypt coincided with volcanic climate disruptions, demonstrating how volcanic effects could ripple across continents to affect distant civilizations. The Greeks and Romans lived intimately with volcanic activity, developing some of humanity's first scientific approaches to understanding these phenomena. Mount Etna in Sicily, Europe's most active volcano, features prominently in Greek mythology as the forge of Hephaestus, the god of fire and metalworking, or as the prison of the monster Typhon. Greek philosophers like Empedocles studied volcanic activity, with legend claiming Empedocles threw himself into Etna's crater to prove his divinity. Aristotle proposed that volcanoes resulted from underground winds, while Seneca suggested they were caused by water entering underground fires. The Romans built extensively in volcanic regions, drawn by fertile soils and natural hot springs, despite obvious dangers. The Bay of Naples, dominated by Mount Vesuvius, became one of the Roman Empire's most prosperous regions. Wealthy Romans built elaborate villas along the coast, while cities like Pompeii and Herculaneum thrived on the rich volcanic soils that supported intensive agriculture. Roman concrete, one of their most important technological innovations, relied on volcanic ash called pozzolana, which when mixed with lime created a cement that could harden underwater and actually grew stronger over time. The eruption of Vesuvius in 79 CE provides our most detailed ancient account of a volcanic disaster preserved in the letters of Pliny the Younger. His uncle, Pliny the Elder, commander of the Roman fleet and noted natural historian, died attempting to rescue friends from the eruption. The younger Pliny's descriptions of the eruption column that rose like an umbrella pine and the darkness that fell like a room when the lamp is put out gave science the term Plinian eruption for similar explosive events. His account captures both the physical phenomena and human responses to the disaster with remarkable clarity. Pompeii and Herculaneum, buried by the Vesuvius eruption, provide unparalleled glimpses into Roman life frozen at a moment of catastrophe. The cities were buried so quickly that organic materials normally lost to decay were preserved. Wooden furniture, scrolls, food, and even the forms of victims were captured in volcanic ash that hardened around them. These sites reveal how Romans lived with volcanic risk, showing evidence of earthquake damage from previous seismic activity that residents had repaired rather than abandoning their homes. Wall paintings depict Vesuvius as a peaceful mountain covered with vineyards, suggesting the volcano had been quiet long enough for people to forget its dangerous nature. In Mesoamerica, volcanoes played central roles in mythology and urban planning. The Aztecs viewed volcanoes as sacred mountains connecting Earth to the heavens, homes of gods and destinations for pilgrimages. Popocatépetl and Iztaccíhuatl, the twin volcanoes visible from their capital Tenochtitlan, featured in creation myths and love stories. The Aztecs made ritual offerings at shrines built near volcanic craters, archaeological evidence of which survives at elevations above 15,000 feet. Volcanic glass was essential for creating the obsidian blades used in weapons, tools, and ritual bloodletting implements central to Mesoamerican religious practices. The Maya civilization also developed in a volcanically active region, with cities like Copan built on volcanic ash deposits. The eruption of Ilopango volcano in El Salvador around 540 CE devastated Maya settlements within 60 miles of the volcano and may have contributed to political upheavals during the classic Maya period. Maya texts describe volcanic eruptions in mythological terms, associating them with divine anger or cosmic battles. They used volcanic materials extensively, from obsidian tools to pumice stones for construction and volcanic ash as temper in pottery production. In Japan, where over 10% of the world's active volcanoes are located, volcanic worship became deeply embedded in Shinto beliefs. Mount Fuji, Japan's highest and most sacred mountain, is revered as the dwelling place of the goddess Konohana-sakuya Hime. Pilgrimage routes established over 1,000 years ago still bring climbers to its summit, combining religious devotion with respect for the volcano's power. Japanese culture developed sophisticated ways of living with volcanic hazards, including architectural techniques for earthquake resistance and agricultural practices that maximize the benefits of volcanic soils while minimizing risks. The indigenous peoples of the Pacific developed sophisticated knowledge of volcanic behavior through generations of observation. In Hawaii, the goddess Pele personified volcanic forces, with elaborate oral traditions describing her travels between islands that accurately reflect the geological progression of volcanic activity along the Hawaiian chain. Offerings to Pele before crossing lava fields or during eruptions represented both religious practice and practical wisdom about volcanic hazards. Traditional Hawaiian chants preserve observations of eruption characteristics that align remarkably well with modern scientific understanding. Indonesian cultures, living in one of the world's most volcanically active regions, developed complex relationships with their fiery mountains. The Javanese view volcanoes as cosmic mountains, connecting the human world with divine realms. Regular ceremonies and offerings aim to maintain balance between human communities and volcanic forces. Traditional knowledge includes recognition of warning signs before eruptions, such as changes in hot springs, animal behavior, and unusual sounds from the mountain. This indigenous knowledge often proved more effective than early scientific monitoring in predicting eruptions and saving lives. The Andean peoples of South America considered volcanoes to be powerful deities or the dwelling places of gods. The Inca made human sacrifices on volcanic peaks, with frozen mummies found at elevations above 20,000 feet on volcanoes like Lulailico. These sacrifices, often children selected for their perfection, were believed to ensure favorable conditions for agriculture and protect communities from volcanic eruptions. The Inca also developed sophisticated techniques for farming on volcanic slopes, creating terraced agricultural systems that maximized the fertility of volcanic soils while preventing erosion. Ancient Chinese civilization, though centered in regions with limited volcanic activity, recorded observations of distant eruptions and their effects. Chinese astronomers noted the dimming of sunlight and unusual atmospheric phenomena following major eruptions, correlating these with poor harvests and social unrest. Chinese traders brought back accounts of volcanoes from Southeast Asia, contributing to mythologies about fire-breathing dragons living beneath mountains. Volcanic materials like sulfur became important in traditional Chinese medicine and later in the invention of gunpowder. The Norse peoples of Iceland, settling a volcanically active island in the 9th century, developed unique cultural adaptations to volcanic hazards. The sagas record numerous eruptions and their impacts on settlement patterns and survival strategies. Volcanic eruptions influenced Norse mythology, with the world-ending Ragnarök possibly inspired by volcanic winters. Icelanders learned to use geothermal heat for bathing and eventually for heating buildings, while volcanic ash renewed pasture soils. The interplay between ice and fire in Icelandic volcanoes created particularly dangerous eruptions that influenced settlement locations and travel routes. Throughout the ancient world, volcanoes inspired religious and philosophical thought about the nature of Earth and divine power. Many cultures interpreted eruptions as expressions of divine anger requiring propitiation through sacrifice and proper behavior. Others saw volcanoes as entrances to underworld realms or workshops of divine craftsmen. These beliefs influenced settlement patterns, agricultural practices, and social hierarchies. Priests and shamans who claimed to interpret or influence volcanic activity held significant power in their societies. The practical knowledge accumulated by ancient peoples living near volcanoes was often remarkably sophisticated. Traditional calendars in some cultures incorporated volcanic cycles, recognizing that certain volcanoes showed periodic behavior. Indigenous names for volcanic features often encoded important information about hazards, with place names warning of dangerous gas emissions, unstable ground, or frequent lava flows. Traditional building techniques in volcanic regions incorporated features to resist earthquake damage and shed volcanic ash, representing engineering solutions developed through trial and error over generations. The benefits that drew ancient peoples to volcanic regions remain relevant today. Volcanic soils support some of the world's most productive agriculture, feeding billions of people. Geothermal energy, first harnessed by ancient peoples for heating and cooking, now provides renewable electricity. Volcanic materials continue to be essential in construction, manufacturing, and technology. The same features that made volcanoes attractive to our ancestors continue to draw modern populations, creating ongoing challenges in managing volcanic risks. The legacy of early human interactions with volcanoes extends beyond practical matters to influence art, literature, and philosophy. Volcanic imagery appears in creation myths worldwide, suggesting deep psychological impacts of witnessing eruptions. The sudden destruction of thriving cities like Pompeii became cautionary tales about hubris and the limits of human power. Volcanic landscapes inspired aesthetic concepts of the sublime, combining beauty with terror in ways that profoundly influenced human culture. The challenge of understanding volcanic phenomena drove early scientific thinking about Earth's structure and processes. As civilizations grew more complex, they developed increasingly sophisticated ways of managing volcanic hazards while exploiting volcanic resources. Trade networks distributed volcanic materials across continents, making obsidian, pumice, and volcanic ash available far from their sources. Agricultural techniques evolved to maximize the fertility of volcanic soils while minimizing erosion and other hazards. Architectural innovations allowed buildings to survive moderate volcanic earthquakes and ashfalls. Religious and civic institutions developed protocols for responding to volcanic crises, including evacuation procedures and disaster relief systems that presaged modern emergency management. For thousands of years, humans watched volcanoes with a mixture of fear and fascination, seeking patterns in their behavior that might reveal when the next eruption would come. Ancient observers noticed that earthquakes often preceded eruptions, that animals fled before volcanic catastrophes, and that hot springs changed temperature or chemistry before the mountain exploded. These observations, passed down through generations as folk wisdom and religious interpretation, represented humanity's first attempts at volcanic prediction. Yet it would take centuries of scientific revolution before these scattered observations coalesced into the modern science of volcanology, where satellites peer through ash clouds, seismometers detect magma movement miles underground, and computers model eruption scenarios with increasing precision. The transformation of volcano observation from mysticism to science began during the Age of Enlightenment, when natural philosophers started systematic documentation of volcanic phenomena. William Hamilton, British envoy to Naples from 1764 to 1800, spent decades observing Vesuvius and the volcanoes of Sicily, producing detailed drawings and descriptions that set new standards for volcanic documentation. His collection of volcanic rocks and minerals, along with his published observations, helped establish volcanology as a legitimate field of scientific inquiry. Hamilton recognized that careful observation over time could reveal patterns in volcanic behavior, noting connections between earthquakes, ground deformation, and subsequent eruptions. The birth of modern volcanology is often traced to the eruption of Krakatoa in 1883, the first major volcanic event to occur in the age of global telecommunications. Telegraph cables carried news of the eruption around the world within hours, while the recently established worldwide network of weather stations recorded the atmospheric pressure waves that circled the globe 7 times. Scientists could correlate observations from multiple locations, recognizing that volcanic effects extended far beyond the immediate vicinity of the eruption. The Royal Society of London's investigation of Krakatoa, published in 1888, became a model for scientific eruption studies, combining eyewitness accounts with instrumental measurements and laboratory analysis of volcanic products. The destruction of Saint-Pierre on Martinique by Mount Pelée in 1902 marked a turning point in understanding volcanic hazards. The eruption introduced the world to pyroclastic flows, those deadly currents of hot gas and volcanic debris that race down volcano slopes at highway speeds. Alfred Lacroix, who studied the eruption in detail, developed the first classification system for different types of volcanic eruptions based on their explosive intensity and the characteristics of their products. His work established that predicting volcanic hazards required understanding not just when a volcano might erupt, but how it might erupt, recognizing that different eruption styles posed vastly different threats. The founding of the Hawaiian Volcano Observatory in 1912 by Thomas Jagger represented a revolutionary approach to volcano science. Rather than studying volcanoes only during eruptions, Jagger established continuous monitoring, recording earthquakes, ground tilting, and volcanic phenomena 24 hours a day, year after year. His philosophy that no more shall the cities be destroyed drove the development of systematic volcano surveillance. The relatively frequent and accessible eruptions of Kilauea provided an ideal natural laboratory where scientists could safely observe volcanic processes and test monitoring techniques that would later be applied to more dangerous volcanoes worldwide. Early volcano monitoring relied on simple but ingenious instruments. Seismometers detected earthquakes by measuring the relative motion between a suspended mass and the moving ground, recording vibrations on smoked paper or photographic film. Tilt meters, often nothing more than water-filled tubes connecting 2 points, detected ground deformation as magma moved beneath the volcano. Temperature measurements of fumaroles and hot springs tracked changes in volcanic heat output. These basic tools, when used systematically over time, began revealing patterns that preceded eruptions, offering the first real possibility of volcanic prediction. The development of seismology as a quantitative science revolutionized volcano monitoring. Scientists learned to distinguish between different types of volcanic earthquakes, each telling a different story about subsurface processes. Long-period earthquakes indicated the movement of fluids, likely magma or gas, through cracks in the rock. Harmonic tremor, a continuous vibration like the hum of a tuning fork, often signaled that magma was moving toward the surface. Volcano-tectonic earthquakes showed rocks breaking under stress as magma forced its way upward. By analyzing the patterns, depths, and frequencies of these different earthquake types, volcanologists could track magma movement from deep storage regions to shallow chambers to the surface. World War II brought technological advances that would transform volcano science. Radar, developed for military purposes, could penetrate volcanic ash clouds to track eruption columns and detect changes in volcano shape. Infrared photography revealed heat patterns invisible to the naked eye, showing where magma approached the surface. Aircraft allowed rapid reconnaissance of remote volcanoes and sampling of eruption clouds. Perhaps most importantly, the war's aftermath brought increased government funding for natural hazard research, recognizing that volcanic eruptions could affect military operations and civilian populations alike. The eruption of Mount St. Helens in 1980 became the most closely monitored volcanic event in history up to that time, providing unprecedented insights into eruption processes. Scientists had 2 months of warning as earthquakes and ground deformation indicated magma rising beneath the volcano. They watched through telescopes and time-lapse cameras as a bulge grew on the volcano's north flank at rates of 5 feet per day. When the eruption finally came, killing 57 people despite the monitoring efforts, it taught harsh lessons about the limitations of prediction and the challenges of translating scientific understanding into effective hazard management. The Mount St. Helens eruption catalyzed advances in volcano monitoring technology and methodology. Scientists recognized that no single monitoring technique provided sufficient information for reliable prediction. Instead, multiple lines of evidence needed to be integrated to understand volcanic behavior. Ground deformation might indicate magma intrusion, but without seismic data, scientists could not determine if the magma was moving toward the surface. Gas emissions might suggest new magma arriving from depth, but without deformation data, the volume and location remained unknown. This recognition drove the development of integrated monitoring networks that combined multiple observation types. Satellite technology opened new frontiers in volcano surveillance, allowing scientists to monitor remote volcanoes that would otherwise go unwatched. Thermal infrared sensors detected heat anomalies that might indicate rising magma or new lava flows. Radar satellites measured ground deformation with millimeter precision, revealing subtle swelling or subsidence that ground-based instruments might miss. Ultraviolet sensors tracked sulfur dioxide emissions, providing information about magma degassing even when clouds obscured visual observations. These space-based tools democratized volcano monitoring, bringing surveillance capabilities to developing nations that could not afford extensive ground-based networks. The Global Positioning System, originally developed for military navigation, became one of volcanology's most powerful tools. Networks of GPS receivers placed around volcanoes could detect ground movements of less than a centimeter, tracking the underground movement of magma in near real time. As magma rose through the crust, it pushed the ground surface upward and outward in characteristic patterns that GPS networks could measure. Combined with computer models of magma chamber geometry, these measurements allowed scientists to estimate the volume and depth of magma intrusions, crucial information for hazard assessment. Gas geochemistry emerged as a critical monitoring technique, recognizing that volcanic gases carried information about deep magmatic processes. The ratios of different gases changed as magma rose and degassed, providing a chemical fingerprint of subsurface conditions. Carbon dioxide, which escapes from magma at great depths, often increased before other signs of unrest appeared. Sulfur dioxide indicated shallower degassing as magma approached the surface. Helium isotope ratios revealed whether new magma was arriving from the deep mantle or, if older, stored magma was remobilizing. These chemical signals, when properly interpreted, provided early warning of changing volcanic conditions. Computer modeling transformed raw monitoring data into useful predictions about volcanic behavior. Numerical models simulated how magma moved through the crust, how eruption columns dispersed ash through the atmosphere, and how pyroclastic flows would travel across topography. These models, constantly refined through comparison with real eruptions, allowed scientists to forecast not just when a volcano might erupt, but where the hazards would be greatest. Probabilistic models acknowledged the inherent uncertainties in prediction, providing decision-makers with risk assessments rather than deterministic forecasts. The human dimension of volcano monitoring proved as important as the technology. The most sophisticated instruments meant nothing if their warnings were not effectively communicated to those at risk. Volcanologists learned to work with emergency managers, developing alert-level systems that translated complex scientific observations into clear action recommendations. They engaged with local communities, incorporating traditional knowledge and addressing cultural concerns about volcanic hazards. The success of an evacuation often depended more on public trust in scientific warnings than on the accuracy of the prediction itself. Several successful predictions demonstrated the life-saving potential of volcano monitoring. The 1991 eruption of Mount Pinatubo in the Philippines, predicted weeks in advance, allowed the evacuation of tens of thousands of people and prevented catastrophic casualties. The 2000 eruption of Mount Usu in Japan was forecast so accurately that tourists gathered at designated viewpoints to watch the eruption begin. These successes built confidence in volcanic prediction while also raising public expectations, sometimes beyond what science could reliably deliver. Yet for every success, volcanoes reminded scientists of the limitations of prediction. Some eruptions occurred with little or no warning, particularly at volcanoes that had been quiet for centuries and lacked monitoring equipment. Other volcanoes showed signs of unrest for years without erupting, causing evacuation fatigue in local populations. Phreatic eruptions caused by groundwater flashing to steam rather than new magma often occurred without precursors that monitoring could detect. These challenges highlighted that volcanic prediction remained as much art as science, requiring experienced interpretation of ambiguous signals. The digital revolution brought artificial intelligence and machine learning to volcano monitoring, offering new ways to process the vast streams of data from modern monitoring networks. Algorithms could identify patterns in seismic data that human analysts might miss, detect subtle changes in satellite imagery, and integrate diverse data types to assess volcanic hazards. Neural networks trained on past eruptions learned to recognize precursory patterns, though the limited number of well-monitored eruptions constrained their training. These tools augmented rather than replaced human expertise, with experienced volcanologists still needed to interpret results and make critical decisions. Modern volcano observatories operate as high-technology nerve centers, continuously processing data from hundreds of instruments. Seismic networks with dozens of stations track earthquake activity in 3 dimensions. GPS networks measure ground deformation with millimeter precision. Infrasound arrays detect atmospheric pressure waves from explosions. Gas sensors sniff volcanic emissions. Thermal cameras watch for temperature changes. All this data flows in real time to observatory computers, where automated systems flag anomalies for human review. During volcanic crises, observatories become round-the-clock operations centers, with teams of scientists analyzing incoming data and updating hazard assessments. The international nature of volcanic hazards fostered global cooperation in volcano monitoring. The World Organization of Volcano Observatories facilitates information sharing between institutions, ensuring that lessons learned at one volcano benefit monitoring efforts worldwide. During major eruptions, international teams of experts converge to assist local scientists, bringing specialized equipment and expertise. Volcanic ash advisories for aviation require coordination between observatories, meteorological agencies, and air traffic control across national boundaries. This collaborative approach recognizes that volcanic hazards do not respect political borders. Famous volcanologists became public figures, their expertise called upon during volcanic crises worldwide. Maurice and Katia Kraft documented active volcanoes for decades before dying in a pyroclastic flow, at Japan's Unzen volcano in 1991, their dramatic footage educating millions about volcanic hazards. David Johnston, who died monitoring Mount St. Helens, became a symbol of scientific dedication to public safety. Haraldur Sigurdsson's studies of past eruptions revealed the global impacts of volcanism on human history. These individuals and many others advanced both the science and public understanding of volcanoes, building the knowledge base for modern prediction efforts. The economic implications of volcanic prediction extend far beyond preventing casualties. False alarms that trigger unnecessary evacuations can cost millions in lost productivity and erode public confidence in future warnings. Failing to predict an eruption can result in lawsuits and criminal charges against responsible scientists, as happened after the 2009 L'Aquila earthquake in Italy. Aviation routes disrupted by volcanic ash cost airlines billions in the 2010 Eyjafjallajökull eruption. These stakes create pressure on volcanologists to balance caution with accuracy, to communicate uncertainty while providing actionable information, and to serve multiple stakeholders with sometimes conflicting needs. Looking forward, volcano monitoring continues evolving with advancing technology. Drone aircraft equipped with sensors fly through eruption columns, sampling gases and particles too dangerous for piloted aircraft to approach. Distributed acoustic sensing turns fiber optic cables into seismometer arrays, thousands of sensors long. Quantum gravimeters detect minute changes in subsurface mass distribution as magma moves. Social media mining algorithms track eyewitness reports of volcanic phenomena, providing real-time ground truth for remote sensing observations. These emerging technologies promise ever-improving volcanic surveillance, though the fundamental challenge of predicting natural processes of enormous complexity remains. The morning of May 8, 1902 began like any other in Saint-Pierre, the pearl of the French Caribbean and Martinique's thriving commercial centre. Ships filled the harbour, their holds laden with rum and sugar bound for European markets. 28,000 residents went about their daily routines, many preparing for the Ascension Day holiday, despite the ash that had been falling from Mount Pelée for days. At 7:52 a.m., the mountain exploded with a force that would redefine scientific understanding of volcanic hazards. A glowing cloud of superheated gas and ash burst from the volcano's flank, racing down the mountain at over 100 miles per hour, reaching the city in less than 3 minutes. Within moments, Saint-Pierre ceased to exist, its population annihilated except for 2 survivors, one of them a prisoner protected by the thick walls of his underground cell. The destruction of Saint-Pierre introduced the world to pyroclastic flows, though scientists would not fully understand what had happened for years. Witnesses on ships in the harbour described a black cloud rolling down the mountain like an avalanche, glowing red from within, destroying everything in its path. Buildings were not simply burned, but blown apart by the hurricane force of the flow. Glass melted, iron bars twisted into fantastic shapes, and human bodies were instantly carbonized. The force was so great that a 3-ton statue was carried 50 feet from its base. This was not the slow-moving lava flow that most people associated with volcanoes, but something far more terrible, a phenomenon that would reshape how scientists and society viewed volcanic hazards. The impact of Saint-Pierre's destruction rippled far beyond Martinique. Insurance companies faced claims that threatened their solvency, leading to new exclusions for volcanic damage that persist in policies today. The French government's response to the disaster, initially denying the scale of destruction for political reasons, contributed to growing distrust of colonial administration. Scientists rushed to study this new type of eruption, with Alfred Lacroix's detailed investigations establishing the term nuée ardente, or glowing cloud, for these deadly flows. The disaster demonstrated that understanding volcanic hazards required more than watching for lava flows, that volcanoes could kill in ways previously unimagined. Less than 2 decades before Saint-Pierre, the eruption of Krakatoa in August 1883 had already shown the world the global reach of volcanic disasters. The Indonesian Volcanoes explosion on August 27th remains one of the loudest sounds in recorded history, heard clearly 3,000 miles away in Rodriguez Island near Mauritius. The pressure wave from the explosion circled the globe 7 times, recorded by barographs worldwide. The eruption column rose 50 miles into the atmosphere, well into the mesosphere, spreading ash around the world and creating spectacular sunsets that inspired artists including Edvard Munch, whose The Scream may have been influenced by the blood-red skies over Norway. The tsunamis generated by Krakatoa's eruption and the collapse of its caldera proved even more deadly than the eruption itself. Waves reaching heights of 120 feet swept away entire coastal towns in Java and Sumatra. The official death toll of 36,000 almost certainly underestimated the true casualties, as entire communities disappeared without trace. Ships were carried miles inland, including the steamship Barrow, deposited in a jungle valley 30 feet above sea level and 2 miles from the coast. The tsunamis reached as far as South Africa, where unusual waves were noted in harbors, demonstrating the ocean-wide impact of major volcanic events. The atmospheric effects of Krakatoa lasted for years, providing the first well-documented example of volcanic climate impact in the industrial age. Global temperatures dropped by as much as 2 degrees Fahrenheit in the year following the eruption. The moon appeared blue or green for months due to ash particles in the atmosphere. Rainfall patterns shifted, causing droughts in some regions and floods in others. Scientists began to understand how volcanic eruptions could affect global climate, though the mechanisms would not be fully understood for another century. The eruption coincided with the early development of global telegraph networks, allowing news to spread worldwide within hours and creating the first truly global media event. Mount Pelée struck again in 1929-1932 with a series of eruptions that, while less deadly than 1902 due to evacuations, provided scientists with unprecedented opportunities to study pyroclastic flows in action. Frank Perret, an American volcanologist, established an observation post dangerously close to the active dome, documenting the formation and collapse of lava spines and the generation of pyroclastic flows. His photographs and measurements became classics of volcanological literature, though his methods were so dangerous that they would be considered unethical today. These observations confirmed that pyroclastic flows resulted from the collapse of eruption columns or lava domes, providing crucial information for predicting these deadly phenomena. The emergence of the Pacific Ring of Fire as a concept helped scientists recognize patterns in volcanic disasters across the Pacific Basin. The 1912 eruption of Novarupta in Alaska, the largest 20th century eruption, fortunately occurred in a remote area, but it demonstrated the scale of eruptions possible along the Pacific Rim. The Valley of 10,000 Smokes created by this eruption preserved a landscape of fumaroles and ash deposits that provided insights into large-scale explosive volcanism. Had this eruption occurred in a populated area, the casualties would have exceeded any volcanic disaster in recorded history. Japan's location along the Ring of Fire made volcanic disasters a recurring theme in its modern history. The 1914 eruption of Sakurajima transformed it from an island to a peninsula, as lava flows filled the strait separating it from Kyushu. The eruption forced the evacuation of the island's 23,000 residents, though most returned to rebuild on the volcanic deposits. This pattern of destruction and rebuilding characterized Japanese responses to volcanic disasters, with communities developing sophisticated strategies for living with volcanic risk while maintaining economic activities that benefited from volcanic resources. The 1985 eruption of Nevado del Ruiz in Colombia created one of the most preventable tragedies in volcanic history. Scientists had warned of increasing activity at the ice-capped volcano and the danger of lahars. volcanic mudflows created when eruptions melt summit ice. Despite these warnings, no comprehensive evacuation plan existed for the town of Armero, located 45 miles from the volcano in a valley known to have been destroyed by lahars in 1595 and 1845. When the eruption began on November 13th, hot pyroclastic flows melted summit glaciers, sending torrents of mud, ice and debris down river valleys at speeds of 30 miles per hour. The lahar reached Armero around 11:30 p.m. when most residents were asleep. The wall of mud, in places 100 feet deep, obliterated the town in minutes. Of the 29,000 residents, 23,000 died, making it the second deadliest volcanic disaster of the 20th century. The tragedy was compounded by the fact that many victims survived the initial impact but died waiting for rescue, trapped in mud that hardened like concrete. The image of 13-year-old Omaira Sanchez, trapped for 3 days before dying as cameras recorded her plight, became an icon of the disaster and raised questions about media ethics and disaster response. Mount St. Helens erupted on May 18, 1980, providing the first major volcanic disaster in the continental United States in living memory. The eruption began when an earthquake triggered the largest landslide in recorded history, removing the volcano's north flank and releasing pressure on the magma beneath. The lateral blast that followed devastated 230 square miles of forest, flattening trees like matchsticks up to 19 miles from the volcano. The eruption column rose 15 miles into the stratosphere, depositing ash across 11 states. Despite 2 months of precursory activity and scientific monitoring, 57 people died, including volcanologist David Johnston, who radioed, "Vancouver, Vancouver, this is it," moments before being killed by the lateral blast. The Mount St. Helens eruption became the most studied volcanic event in history, revolutionizing understanding of explosive volcanism. Scientists documented the lateral blast, a previously unrecognized hazard that could devastate areas thought safe from vertical eruptions. The biological recovery of the blast zone provided insights into ecological succession after catastrophic disturbance. The economic impact, exceeding $1 billion, demonstrated the vulnerability of modern infrastructure to volcanic hazards. The eruption also revealed challenges in managing volcanic crises, as conflicts between scientific recommendations, economic interests, and individual freedom complicated evacuation efforts. The 1991 eruption of Mount Pinatubo in the Philippines represented both a triumph of volcanic prediction and a demonstration of the global impacts of major eruptions. After 600 years of dormancy, the volcano showed signs of unrest in March 1991. International cooperation between Philippine and American scientists, motivated partly by the presence of Clark Air Base nearby, led to successful prediction of the June 15th climactic eruption. The evacuation of 60,000 people from the danger zone prevented massive casualties, though post-eruption lahars killed hundreds in subsequent years as monsoon rains remobilized volcanic deposits. Pinatubo injected 20 million tons of sulfur dioxide into the stratosphere, the largest stratospheric perturbation since Krakatoa. Global temperatures dropped by 1 degree Fahrenheit for 2 years, temporarily masking the greenhouse warming trend. The ozone layer thinned, with the Antarctic ozone hole reaching record size. The eruption coincided with Typhoon Yunya, whose rains mixed with falling ash to collapse roofs across central Luzon, adding to the destruction. Clark Air Base was abandoned, ending nearly a century of American military presence and causing economic disruption that persisted for decades. The ongoing eruption of Soufriere Hills volcano on Montserrat, beginning in 1995, transformed the Caribbean island from a tropical paradise to a volcanic disaster zone. The capital, Plymouth, was gradually buried under pyroclastic flows and lahars, becoming a modern Pompeii. 2/3 of the island's 12,000 residents fled, creating a diaspora that fundamentally altered Montserratian society. The eruption's long duration, continuing intermittently for over 2 decades, challenged traditional disaster response models designed for acute crises rather than chronic volcanic activity. Indonesia's position along the Ring of Fire made it the site of numerous modern volcanic disasters. The 2010 eruption of Merapi killed over 300 people despite extensive monitoring and evacuation efforts, demonstrating the challenges of managing volcanic risk in densely populated areas. The 2018 eruption of Anak Krakatau, the child of Krakatoa that emerged from the sea in 1927, triggered a tsunami that killed over 400 people, showing that the hazards that devastated the region in 1883 remained active threats. The 2010 eruption of Eyjafjallajökull in Iceland, while causing no direct casualties, created the largest disruption to air travel since World War II. The relatively small eruption injected fine ash into jet stream altitudes, forcing the closure of European airspace for 6 days. Over 100,000 flights were cancelled, stranding millions of passengers and costing airlines over $1 billion. The crisis revealed the vulnerability of modern aviation to volcanic ash and led to new protocols for managing airspace during volcanic eruptions. The difficulty pronouncing the volcano's name became a global joke, highlighting how volcanic hazards had entered mainstream consciousness. Recent eruptions have demonstrated that volcanic disasters are not merely natural events, but complex interactions between geological processes and human systems. The 2002 eruption of Nyiragongo in the Democratic Republic of Congo sent lava flows through the city of Goma, destroying 14,000 homes and forcing 350,000 people to flee. The disaster was exacerbated by ongoing civil conflict, poverty, and weak governance that hampered response efforts. Similarly, the 2010 Merapi eruption's impact was amplified by demographic pressure that pushed settlements ever closer to the volcano despite known hazards. The increasing connectivity of the modern world means that volcanic impacts ripple globally through supply chains and transportation networks. The 2011 eruption of Puyehue Cordon Caule in Chile disrupted air travel across the southern hemisphere for weeks. Volcanic ash from various eruptions has repeatedly threatened jet aircraft, with several near disasters when planes encountered ash clouds. The economic losses from flight cancellations often exceed the direct damage from eruptions, demonstrating how modern society's complexity creates new vulnerabilities to ancient hazards. Climate change adds new dimensions to volcanic hazards as melting glaciers on volcanic peaks increase the risk of lahars, and changing precipitation patterns affect the stability of volcanic deposits. The retreat of ice caps on volcanoes like Cotopaxi in Ecuador exposes unstable volcanic deposits to erosion, potentially triggering destructive debris flows without any new eruption. Rising sea levels increased tsunami risks from volcanic island collapses. These evolving hazards require continuous reassessment of volcanic risks in a changing world. Modern communications technology has transformed how volcanic disasters unfold in public consciousness. Social media spreads images and videos of eruptions instantly worldwide, creating global awareness but also spreading misinformation. Live webcams allow anyone to monitor active volcanoes in real time, democratizing volcano observation but sometimes encouraging dangerous tourism. The 24-hour news cycle demands constant updates during volcanic crises, pressuring scientists to make pronouncements before full analysis is complete. These changes have made volcanic disasters as much media events as natural phenomena. The professionalization of emergency management has improved responses to volcanic disasters with standardized procedures, international cooperation frameworks, and specialized response teams. The volcanic ash advisory centers, established after several aviation incidents, provide global monitoring of ash hazards to aviation. The International Association of Volcanology and Chemistry of the Earth's interior coordinates scientific response to volcanic crises. These institutions represent humanity's organized attempt to manage volcanic hazards, though each eruption reveals new challenges and gaps in preparedness. Looking at the pattern of modern volcanic disasters, several themes emerge. The deadliest eruptions often occur at volcanoes that have been dormant for generations, where collective memory of past disasters has faded. Pyroclastic flows and lahars cause more deaths than lava flows or ash falls, yet public perception still focuses on flowing lava as the primary volcanic hazard. Secondary effects, particularly lahars remobilizing volcanic deposits years after eruptions, often cause more prolonged suffering than the eruptions themselves. Political and economic factors frequently override scientific recommendations, leading to preventable casualties. Every morning, Maria tends her coffee plants on the slopes of Volcán de Fuego in Guatemala, the rich volcanic soil yielding beans that will eventually reach cups in distant cities around the world. Behind her modest farm, the volcano sends up its daily plume of smoke, a reminder of the bargain her family made generations ago when they first settled this land. The soil that nourishes their crops exists only because of countless eruptions over millennia, each one adding another layer of mineral-rich ash to the mountainside. When asked why she stays despite the danger, despite the evacuation orders that come every few years, she gestures to the green abundance around her and says simply that the mountain gives more than it takes. This paradox defines life for the 800 million people worldwide who live within 60 miles of an active volcano. They are not ignorant of the risks, nor are they fatalistic about their chances. Instead, they have made calculated decisions, weighing danger against opportunity, temporary hazard against permanent benefit. The very features that make volcanoes dangerous also make them attractive for human settlement. Their eruptions create the fertile soils that support intensive agriculture. Their elevation provides refuge from lowland heat and disease. Their scenic beauty draws tourists whose spending supports entire economies. Understanding why people live near volcanoes requires looking beyond simple risk assessment to consider the complex web of factors that tie communities to these dangerous landscapes. The fertility of volcanic soils stands as the primary attraction that has drawn farmers to volcanic regions throughout history. Fresh volcanic ash contains a cocktail of essential plant nutrients released as the ash weathers: phosphorus, potassium, calcium, magnesium, and trace elements become available to plants in proportions ideally suited for agriculture. The physical properties of volcanic soils also favor farming, with excellent water retention balanced by good drainage and a structure that resists compaction. In Java, where volcanic soils support some of the highest rural population densities on Earth, farmers can harvest 3 rice crops per year from fields that have been continuously cultivated for centuries without exhaustion. The economic mathematics of volcanic agriculture often overwhelm safety concerns. In Indonesia, farmers on the slopes of Merapi can earn 3 times what they would make farming non-volcanic soils in other regions. Coffee grown on volcanic slopes commands premium prices in international markets, with volcanic terroir considered essential for the finest beans. In Italy, wines from volcanic soils around Vesuvius and Etna fetch prices that would be impossible for grapes grown elsewhere. These economic realities create powerful incentives for people to remain in hazardous areas, viewing occasional evacuations as acceptable costs for ongoing prosperity. Beyond agriculture, volcanoes provide numerous resources that support local economies. Volcanic rock makes excellent construction material, from the lightweight pumice used in concrete blocks to the hard basalt that paves roads. Sulfur deposits around volcanic vents support mining operations, while volcanic sand and gravel feed the construction industry's endless appetite for aggregate. In Japan, Indonesia, and Latin America, entire industries depend on extracting and processing volcanic materials, creating employment for millions who might otherwise face poverty. Geothermal energy represents one of the most valuable gifts of volcanic regions, providing renewable power and heat to communities fortunate enough to live near suitable resources. Iceland generates nearly all its electricity and heating from volcanic geothermal sources, transforming what could be a marginal Arctic island into a prosperous modern nation. The Philippines derives 14% of its electricity from geothermal plants clustered around volcanoes. Kenya has become a geothermal powerhouse in Africa, with plants around the East African Rift providing reliable baseload power. These energy resources create jobs, attract industry, and provide energy independence that would be impossible without volcanic heat. Tourism drawn by volcanic landscapes generates billions in annual revenue, supporting entire regional economies. Mount Fuji attracts over 300,000 climbers annually, while millions more visit just to view and photograph the iconic peak. Hawaii's volcano tourism contributes over $2 billion yearly to the state economy. The Roman ruins of Pompeii and Herculaneum, preserved by Vesuvius's eruption, draw 3 million visitors annually. Even active eruptions become tourist attractions, with travelers flocking to see lava flows and eruption columns, creating booms for local hotels, restaurants, and guide services. The establishment of communities near volcanoes often reflects historical momentum as much as conscious choice. Many volcanic regions were settled centuries or millennia ago, when populations were smaller and alternative locations scarce. Over generations, these communities develop deep cultural, social, and economic roots that make relocation unthinkable for many residents. Ancestral lands, family graves, religious sites, and community networks create attachments that transcend rational risk assessment. In many cultures, the volcano itself becomes part of community identity, featured in local mythology, art, and tradition in ways that make separation psychologically difficult. Urban development patterns around volcanoes reveal how cities can become trapped by their own success. Naples, with 3 million people living in the shadow of Vesuvius, started as a small Greek colony attracted by the harbor and fertile soils. Each generation built upon the previous one's infrastructure, creating accumulated investment too valuable to abandon. Modern Quito sprawls across volcanic terrain that seemed safely distant when the city was founded, but now places 2 million people at risk. These cities face seemingly impossible choices between protecting enormous populations and maintaining economic activities that support millions of livelihoods. The concept of acceptable risk varies dramatically between cultures and individuals, shaped by experience, economic status, and psychological factors. Communities that have lived with volcanic hazards for generations often develop sophisticated understanding of their local volcano's behavior, recognizing warning signs and knowing when real danger threatens versus routine activity. This indigenous knowledge, passed down through oral traditions and collective memory, sometimes proves more accurate than scientific assessments. On Merapi in Java, traditional spiritual guardians called Juru Kunci maintain elaborate systems of volcanic interpretation that blend empirical observation with spiritual practice, often successfully predicting eruptions. Poverty constrains choices for many living near volcanoes, making risk tolerance a luxury they cannot afford to consider. Landless farmers in the Philippines may understand that living on the slopes of Mayon volcano is dangerous, but without alternatives, they accept the risk as preferable to certain starvation. Slum dwellers in Goma, Democratic Republic of Congo, build shanties on recent lava flows from Nyiragongo, not from ignorance, but from desperation, as even dangerous land is better than no land at all. For these populations, volcanic hazards represent just one of many daily survival challenges, often less immediate than poverty, disease, or violence. Technological advances have made living near volcanoes somewhat safer, while paradoxically encouraging more development in hazardous areas. Modern monitoring systems provide warnings that allow temporary evacuations while minimizing economic disruption. Hazard mapping identifies relatively safe zones for development. building codes mandate construction techniques resistant to ash loading and seismic shaking. Insurance and disaster relief programs cushion economic losses. These risk reduction measures create a sense of security that may be partially justified, but can also encourage development in areas that remain fundamentally hazardous. The Japanese approach to volcanic coexistence represents perhaps the most sophisticated adaptation to volcanic hazards. With 111 active volcanoes in a densely populated nation, complete avoidance is impossible. Instead, Japanese society has developed comprehensive strategies for living with volcanic risk. Detailed hazard maps guide land use planning. Regular evacuation drills maintain readiness. Volcanic observatories monitor every active volcano. Building codes require ash-resistant roofs and air filtration systems. School curricula include volcanic hazard education. This systematic approach allows millions to live and work near volcanoes while minimizing casualties. Community resilience in volcanic regions often surpasses that in less hazardous areas, as repeated exposure to volcanic threats builds social capital and adaptive capacity. Neighbors develop strong mutual aid networks, knowing they may need to rely on each other during crises. Local governments maintain evacuation plans and emergency supplies. Traditional festivals and religious ceremonies reinforce community bonds while transmitting hazard knowledge. These social structures, developed in response to volcanic threats, prove valuable for managing other challenges, from economic downturns to climate change. The psychological dimensions of living with volcanic hazards reveal complex cognitive processes that allow people to function despite constant background threat. Optimism bias leads people to believe they are less likely than others to experience negative events. Normalization of risk occurs as daily exposure to volcanic hazards makes them seem routine rather than exceptional. Cognitive dissonance reduction allows people to minimize perceived risk to align with their choice to remain. These psychological mechanisms, while potentially dangerous, provide essential emotional protection that makes life in volcanic regions psychologically sustainable. Religious and spiritual relationships with volcanoes profoundly influence how communities perceive and respond to volcanic hazards. Many cultures view volcanoes as sacred mountains, homes of deities or ancestors whose moods determine eruption patterns. In Bali, elaborate ceremonies maintain proper relationships with volcanic deities, providing psychological comfort and reinforcing community cohesion. Christian communities in Latin America often interpret eruptions as divine tests or punishments, finding meaning that helps process trauma. These spiritual frameworks, while sometimes conflicting with scientific hazard assessment, provide crucial emotional and social resources for managing volcanic risk. Economic entanglement makes volcanic regions increasingly difficult to abandon as development progresses. Infrastructure investments in roads, power lines, water systems, and communications networks represent sunk costs that governments are reluctant to write off. Industrial facilities located to take advantage of geothermal energy or volcanic materials cannot easily relocate. Agricultural investments in terracing, irrigation, and processing facilities tie communities to specific locations. Property values that represent most families' wealth would collapse if volcanic hazards were fully acknowledged. These economic realities create powerful constituencies opposed to acknowledging or acting on volcanic risks. Climate change intersects with volcanic hazards in ways that complicate risk assessment for communities near volcanoes. Changing precipitation patterns affect lahar hazards, potentially mobilizing old volcanic deposits during extreme rainfall events. Melting glaciers on volcanic peaks alter water resources that communities depend upon. Rising temperatures make higher elevation volcanic slopes more attractive for agriculture and settlement, potentially exposing more people to volcanic hazards. Sea level rise threatens low-lying coastal areas near volcanic islands, reducing refuge options during eruptions. These evolving conditions require communities to continuously reassess and adapt their volcanic risk strategies. The role of government in managing volcanic risk varies dramatically between countries, influencing how communities adapt to volcanic hazards. In wealthy nations, governments typically take primary responsibility for monitoring, warning systems, and disaster response, potentially creating dependency that reduces community self-reliance. In developing countries, limited government capacity forces communities to develop their own risk management strategies, potentially building resilience but also leaving gaps in protection. Corruption and political manipulation of volcanic hazards can undermine both scientific credibility and community preparation, as seen when politicians downplay risks to avoid economic disruption or exaggerate them for political advantage. Insurance and disaster assistance programs create complex incentives that influence settlement patterns near volcanoes. Subsidized insurance can encourage development in hazardous areas by reducing the financial consequences of volcanic damage. Post-disaster aid, while humanitarian necessity, can create moral hazard by allowing people to rebuild in the same hazardous locations. The expectation of government assistance may reduce individual and community investment in risk reduction. Conversely, the absence of insurance or aid in many developing countries forces communities to develop robust self-help mechanisms that may prove more sustainable. Gender dimensions of volcanic risk reveal how hazards affect different populations unequally. Women often bear disproportionate burdens during volcanic crises, responsible for children, elderly relatives, and household belongings during evacuations. Economic opportunities in volcanic regions may differentially benefit men through construction and mining work, while women engage in agriculture that ties them to specific lands. Traditional knowledge about volcanic hazards may be gendered, with women's observations of environmental changes sometimes dismissed despite their accuracy. Understanding these differential impacts is crucial for developing equitable risk reduction strategies. Children growing up near volcanoes develop unique relationships with volcanic hazards that shape lifelong risk perception. Regular evacuation drills in school normalize volcanic threats while building practical response skills. Volcanic features in daily landscapes become familiar rather than threatening. Stories from parents and grandparents about past eruptions transmit both hazard knowledge and coping strategies. This childhood socialization creates adults who are neither paralyzed by volcanic risks nor dismissive of them, but rather capable of living productive lives while maintaining appropriate vigilance. The future of human habitation near volcanoes will likely see continued growth despite known hazards. Population pressure in many countries leaves few alternatives to volcanic lands. Climate change may make volcanic highlands more attractive as lowlands become unbearably hot. Technological advances in monitoring and warning systems provide confidence, whether justified or not, that volcanic risks can be managed. Economic globalization creates markets for volcanic products, from agriculture to tourism, that incentivize continued habitation. Understanding and managing this continued coexistence with volcanic hazards represents one of the 21st century's ongoing challenges. The wisdom accumulated by communities living near volcanoes offers lessons extending beyond volcanic hazards. Their experience demonstrates human capacity to adapt to seemingly impossible conditions through combinations of traditional knowledge, social organization, technological innovation, and psychological resilience. They show that risk is never simply about physical hazard, but always mediated by social, economic, cultural, and political factors. Their strategies for maintaining normal life despite abnormal threats provide models for adapting to other 21st century challenges, from climate change to technological risks. In choosing to live in the shadow of volcanoes, these communities embody the fundamentally human trait of choosing hope over fear, opportunity over security, and life over mere survival. In 1979, a small spacecraft named Voyager 1 sailed past Jupiter and its moons, carrying cameras that would revolutionize our understanding of volcanism in the cosmos. As the probe photographed Io, Jupiter's innermost large moon, navigation engineer Linda Morabito noticed something extraordinary in one image, a strange umbrella-shaped plume rising nearly 200 miles above the moon's surface. This was humanity's first observation of an active volcano beyond Earth, a discovery that shattered assumptions about where volcanism could exist and opened our eyes to a universe filled with volcanic worlds far stranger than anything imagined. The volcanoes of Io exceeded all expectations, erupting with a violence and frequency that makes Earth's most active volcanoes seem dormant by comparison. This moon, roughly the size of Earth's moon, hosts over 400 active volcanoes with eruptions so powerful they can be observed by telescopes on Earth, 400 million miles away. Lava fountains on Io reach heights that would tower over Mount Everest, propelled by volcanic gases escaping at speeds exceeding 2,000 miles per hour. The entire surface of Io renovates itself through volcanic eruptions every few centuries, erasing impact craters and creating a world that looks younger than any other body in the solar system. The mechanism driving Io's extreme volcanism reveals how different volcanic processes can be on other worlds. Jupiter's immense gravity creates tides in Io's solid rock that rise and fall by 300 feet, more than 5 times the height of Earth's ocean tides. As Io orbits Jupiter in an elliptical path, these tidal forces constantly squeeze and stretch the moon's interior, generating friction that melts rock through mechanical heating rather than radioactive decay. This tidal heating produces 100 times more internal energy than radioactive heating generates in Earth, creating a world where volcanism is not an occasional hazard, but the dominant force shaping the entire moon. The composition of Io's volcanism tells us that not all volcanic worlds erupt the same materials. While some of Io's volcanoes produce basaltic lavas similar to those on Earth, others erupt sulfur and sulfur dioxide, creating a palette of colors that makes Io look like a cosmic pizza. Red, yellow, orange, black, and white deposits paint the surface in patterns that change constantly as new eruptions cover old deposits. Some lavas on Io may be ultramafic compositions that erupted on Earth only billions of years ago when our planet's interior was much hotter. Temperature measurements of active lava flows on Io exceed 2,900 degrees Fahrenheit, hotter than any contemporary terrestrial lava, and approaching temperatures that existed during Earth's earliest history. Mars, our nearest planetary neighbor, preserves a volcanic record that dwarfs anything on Earth. Olympus Mons, the largest volcano in the solar system, rises 16 miles above the surrounding plains, nearly 3 times the height of Mount Everest above sea level. This single volcano covers an area the size of Italy, with a summit caldera that could swallow metropolitan London. The sheer size of Martian volcanoes reflects fundamental differences in how volcanism operates on a planet with lower gravity and no plate tectonics. Without moving plates to distribute volcanic activity across multiple locations, single volcanic centers on Mars could remain active for hundreds of millions of years, building enormous structures impossible on Earth. The volcanic province of Tharsis on Mars represents the largest volcanic accumulation in the solar system, a bulge in the planet's crust over 2,500 miles across and up to 6 miles high. This enormous volcanic pile contains enough lava to cover Earth's entire surface to a depth of nearly 30 feet. The formation of Tharsis fundamentally altered Mars's rotation and climate, possibly triggering a true polar wander that shifted the entire crust relative to the rotation axis. The weight of Tharsis created a network of canyons and fractures, including Valles Marineris, a canyon system that stretches for 2,500 miles, 10 times longer and 5 times deeper than the Grand Canyon. Evidence suggests that Mars's volcanoes, while ancient, may not be entirely extinct. Fresh-looking lava flows on the flanks of Olympus Mons appear to be only a few million years old, yesterday, in geological terms. Methane detected in Mars's atmosphere could originate from volcanic outgassing, though biological sources remain possible. Impact craters that should statistically exist on some lava flows are mysteriously absent, suggesting these flows might be younger than previously thought. While no active eruption has been observed on Mars, the possibility of future volcanism cannot be ruled out, raising intriguing questions about the potential for volcanic heat to create habitable environments beneath the Martian surface. Venus, Earth's twin in size, reveals a volcanic history dramatically different from our planet despite similar bulk composition. The surface of Venus, mapped by radar through its thick atmosphere, shows over 1,600 major volcanoes and hundreds of thousands of smaller volcanic features. Unlike Earth, where volcanism concentrates along plate boundaries, Venus's volcanoes scatter seemingly randomly across the surface, suggesting a different mechanism for heat loss from the interior. The planet's surface age, estimated at only 300 to 600 million years based on crater counting, indicates a catastrophic resurfacing event that may have involved planet-wide volcanic flooding. Recent observations suggest Venus might be volcanically active today. Infrared cameras have detected hotspots that could represent active lava flows. Changes in atmospheric sulfur dioxide concentrations might indicate ongoing volcanic outgassing. Some volcanic features appear so fresh that they must have formed recently, lacking the weathering that Venus's corrosive atmosphere should produce over millions of years. If confirmed, active volcanism on Venus would make it only the third body in the inner solar system with confirmed contemporary volcanic activity, joining Earth and Io in this exclusive club. The extreme conditions on Venus create volcanic phenomena impossible on Earth. With surface temperatures of 860 degrees Fahrenheit and atmospheric pressure 90 times that of Earth, the distinction between liquid lava and solid rock becomes blurred. Some models suggest that rocks on Venus might actually flow like glaciers at these temperatures, creating features that look volcanic but form through solid-state creep rather than melting. The high atmospheric pressure suppresses gas exsolution from magma, potentially allowing lava flows to travel much farther than they would on Earth before solidifying. Beyond the realm of molten rock volcanism lies an even stranger phenomenon found on the icy moons of the outer solar system. Cryovolcanism, the eruption of water, ammonia, methane, and other volatile compounds that play the role of molten rock on these frozen worlds, operates throughout the outer solar system. On Saturn's moon, Enceladus, geysers spray water ice and organic compounds hundreds of miles into space from fractures near the South Pole. These eruptions, powered by tidal heating similar to Io's, but at much lower temperatures, feed Saturn's E-ring with fresh material and hint at a subsurface ocean that might harbor conditions suitable for life. Titan, Saturn's largest moon, exhibits cryovolcanic features that mirror terrestrial volcanoes in form, but not composition. Radar images reveal dome-like structures, flow features, and possible volcanic calderas where liquid methane and water ammonia slurries might erupt. At Titan's surface temperature of negative 290 degrees Fahrenheit, water ice behaves like rock, while methane and ethane play the role of water, creating a bizarre parody of Earth's hydrological cycle. Some scientists propose that cryovolcanism on Titan could provide the methane that maintains the moon's thick atmosphere, which should otherwise be destroyed by solar radiation over geological time. Neptune's moon, Triton, displays some of the solar system's most unusual volcanic activity. Dark geysers, observed by Voyager 2, shoot nitrogen gas and dark particles 5 miles high into Triton's thin atmosphere. These eruptions, powered by seasonal heating as transparent nitrogen ice creates a greenhouse effect over dark subsurface materials, represent volcanism driven by temperature differences of only a few degrees. The discovery of active geology on such a cold, distant world expanded concepts of volcanism beyond anything previously imagined. The dwarf planet Pluto surprised scientists with evidence of possible cryovolcanism, when New Horizons flew past in 2015. Mountains of water ice that appear to be cryovolcanoes rise from smooth plains of nitrogen ice. Wright Mons and Picard Mons, each over 100 miles across and 13,000 feet high, lack impact craters, suggesting geologically recent activity. How a body as small and cold as Pluto could maintain volcanic activity billions of years after its formation remains a mystery, challenging models of planetary thermal evolution. Europa, Jupiter's ice-covered moon, might host the solar system's most important volcanism for astrobiology. Beneath its icy shell lies a global ocean containing more water than all Earth's oceans combined. Tidal heating from Jupiter might drive seafloor volcanism in this hidden ocean, potentially creating hydrothermal vents similar to those that some scientists believe sparked life on Earth. Plumes of water vapor detected sprouting from Europa's surface could provide samples of this ocean for future spacecraft to analyze without needing to drill through miles of ice. The asteroid Vesta, visited by the Dawn spacecraft, revealed ancient volcanic features on a body once thought too small for such activity. Vesta's volcanic rocks, sampled through meteorites that fell to Earth, show that even asteroids could differentiate and produce volcanism early in solar system history. These eucrite and diogenite meteorites provide samples of extraterrestrial volcanic rocks that scientists can study in laboratories, revealing details about volcanic processes on other worlds that remote observations cannot provide. The study of extraterrestrial volcanism provides crucial insights into planetary evolution throughout the cosmos. Volcanism represents one of the primary mechanisms by which planets lose internal heat, shaping their surfaces and atmospheres over billions of years. The presence or absence of volcanism determines whether a planet can maintain an atmosphere, regulate its climate through volcanic outgassing and weathering cycles, and potentially support life. Understanding how volcanism operates under different conditions of gravity, atmospheric pressure, and composition helps scientists predict what might exist on planets orbiting other stars. Comparative planetology reveals that Earth's style of volcanism, dominated by plate tectonics, might be unusual rather than typical. Most volcanic worlds appear to lose heat through other mechanisms, whether the hotspot volcanism seen on Mars and Venus, the tidal volcanism of Io and Enceladus, or the cryovolcanism of outer solar system moons. Each world's unique combination of size, composition, and heating mechanisms creates distinct volcanic expressions that expand our understanding of geological processes. The search for volcanism on exoplanets represents the next frontier in understanding cosmic volcanism. Although current technology cannot directly observe volcanic eruptions on planets orbiting other stars, volcanic outgassing might be detectable in exoplanet atmospheres. Sulfur compounds, volcanic aerosols, or the chemical disequilibrium created by volcanic emissions could provide signatures of active volcanism light years away. Some super-Earth exoplanets might experience extreme volcanism unlike anything in our solar system, with their higher gravity and internal pressures creating novel volcanic phenomena. Future missions to volcanic worlds promise revolutionary discoveries about extraterrestrial volcanism. The Europa Clipper mission will investigate the potential for seafloor volcanism in Europa's ocean. The Dragonfly mission to Titan will explore possible cryovolcanic features up close. Proposed missions to Io would observe its extreme volcanism directly, while sample return missions from Mars could bring volcanic rocks to Earth for detailed analysis. Each mission adds pieces to the puzzle of how volcanism shapes worlds throughout the universe. The implications of extraterrestrial volcanism extend beyond scientific curiosity to practical considerations for future space exploration. Volcanic materials on the Moon and Mars could provide resources for future human settlements, from construction materials to water extracted from volcanic minerals. Volcanic caves could shelter astronauts from radiation. Volcanic heat sources might power future bases on icy moons. Understanding and utilizing extraterrestrial volcanism will be crucial for humanity's expansion beyond Earth. The discovery of volcanism throughout the solar system transformed our perspective on Earth's volcanic activity. We now understand that terrestrial volcanism represents just one variation among many possible expressions of planetary heat loss. The sulfur volcanoes of Io, the giant shields of Mars, the cryovolcanoes of Enceladus, and the nitrogen geysers of Triton reveal a universe where the principle of volcanism manifests in forms limited only by the imagination of nature. Each world tells its own volcanic story, written in lava, ice, and gases across landscapes, alien yet oddly familiar. Looking at Earth from this cosmic perspective, we see our planet's volcanism as part of a universal process that shapes worlds throughout the universe. The same fundamental physics that drives eruptions on Earth operates throughout the cosmos, though expressed in wonderfully diverse ways depending on local conditions. The volcanoes that seem so powerful and unique from our terrestrial viewpoint are revealed as one movement in a vast cosmic symphony of planetary evolution, where worlds across the universe exhale their internal heat through volcanic vents, building mountains, atmospheres, and possibly the conditions for life among the stars. The year 1815 began with no indication that humanity was about to experience one of the most significant climate events in recorded history. On April 10th, Mount Tambora in Indonesia exploded with a force that ejected 12 cubic miles of rock and ash into the stratosphere, creating an atmospheric veil that would circle the globe and alter weather patterns on every continent. The following year, 1816, became known as the Year Without a Summer, when snow fell in June across New England, crops failed across Europe, and famine stalked nations already exhausted by the Napoleonic Wars. This single volcanic eruption demonstrated with terrible clarity how volcanism could reshape global climate, a lesson that resonates with new urgency as humanity grapples with anthropogenic climate change, and some scientists propose volcanic geoengineering as a potential solution. The relationship between volcanoes and climate operates through mechanisms that scientists have only recently begun to fully understand. When major eruptions inject sulfur dioxide into the stratosphere, the gas combines with water vapor to form tiny droplets of sulfuric acid. These aerosol particles, smaller than the wavelength of visible light, scatter incoming solar radiation back to space while allowing Earth's infrared radiation to escape, creating a net cooling effect. A single large eruption can reduce global average temperatures by 1 to 3 degrees Fahrenheit for several years, with regional effects that can be far more extreme. The distribution of these aerosols depends on atmospheric circulation patterns, the latitude of the eruption, and the season, creating complex climate responses that continue to challenge prediction models. The 20th century provided several natural experiments in volcanic climate modification that helped scientists understand these processes. The 1963 eruption of Mount Agung in Indonesia cooled global temperatures by about 0.5 degree Fahrenheit. The 1982 El Chichon eruption in Mexico, though smaller than many historical eruptions, occurred at a time when satellite observations and atmospheric monitoring networks could track the spread and effects of volcanic aerosols in unprecedented detail. The 1991 eruption of Mount Pinatubo provided the clearest demonstration yet, cooling global temperatures by nearly 1 degree Fahrenheit and temporarily slowing the rate of human-caused global warming. These volcanic climate impacts have inspired controversial proposals for deliberate climate intervention through artificial volcanic simulation. Some scientists suggest that injecting sulfur compounds into the stratosphere could counteract greenhouse warming, essentially creating controlled volcanic winters to offset human carbon emissions. The technology to accomplish this already exists in the form of high-altitude aircraft or balloons that could release sulfur dioxide or other reflective particles at stratospheric heights. The cost, estimated at only billions of dollars annually, seems trivial compared to the economic impacts of unmitigated climate change. Yet the risks and uncertainties of such intervention generate fierce debate about humanity's right and ability to deliberately modify Earth's climate system. The parallels between volcanic eruptions and proposed geoengineering schemes reveal both opportunities and dangers. Volcanic eruptions demonstrate that stratospheric aerosols can indeed cool the planet, but they also show the limitations and side effects of this approach. The cooling from volcanic aerosols lasts only a few years, requiring continuous injection to maintain the effect. Regional impacts vary dramatically, with some areas experiencing drought while others face flooding. Volcanic aerosols can damage the ozone layer, as observed after major eruptions. The Asian monsoon, upon which billions depend for agriculture, weakens following major volcanic eruptions, raising concerns about geoengineering impacts on global food security. Beyond climate intervention, volcanoes will continue to pose direct hazards that may intensify as human populations grow and concentrate in vulnerable areas. By 2100, over 1 billion people are projected to live within 60 miles of active volcanoes, double the current number. Many of the fastest-growing cities in Asia, Africa, and Latin America sit near volcanic hazards, often with inadequate monitoring and preparedness systems. The increasing interconnection of global systems means that future volcanic eruptions could trigger cascading failures in transportation, communication, finance, and supply chains that amplify far beyond the immediate disaster zone. The next supervolcanic eruption represents an inevitable but unpredictable future catastrophe that humanity must eventually face. Yellowstone, Toba, Campi Flegrei, and other supervolcanoes will erupt again, though whether in hundreds, thousands, or hundreds of thousands of years remains unknown. The impacts of such an eruption on modern civilization would exceed anything in human experience. Agricultural systems optimized for stable climate conditions would collapse under sudden volcanic cooling. Global supply chains dependent on just-in-time delivery would shatter. Political systems already stressed by inequality and climate change might not survive the additional pressure of volcanic catastrophe. Preparing for supervolcanic eruptions challenges conventional disaster planning, which typically focuses on events likely within political or economic planning horizons. No government budgets for catastrophes that might not occur for millennia, yet the consequences of being unprepared could end civilization as we know it. Some scientists advocate for food stockpiles, seed banks, and underground shelters that could preserve human knowledge and genetic diversity through a volcanic winter. Others argue that resources should focus on more probable near-term threats. This debate reflects fundamental questions about how societies should balance current needs against potentially existential but highly uncertain future risks. Underwater volcanoes represent an underappreciated aspect of Earth's volcanic future. 3/4 of Earth's volcanic activity occurs beneath the oceans, mostly along mid-ocean ridges where new seafloor continuously forms. As sea levels rise due to climate change, the reduced pressure on underwater volcanoes could trigger increased eruptions, though the magnitude of this effect remains debated. Submarine volcanic eruptions can generate tsunamis, create new islands, and release enormous quantities of carbon dioxide directly into the oceans, contributing to ocean acidification. The 2022 eruption of Hunga Tonga Hunga Hapai demonstrated that submarine volcanoes could produce atmospheric effects as significant as their subaerial counterparts. The emergence of new volcanic islands offers glimpses of geological processes normally hidden beneath the waves. Surtsey, which emerged off Iceland in 1963, provided scientists with a natural laboratory to study how life colonizes virgin volcanic terrain. Within years, plants, birds, and invertebrates established themselves, demonstrating life's remarkable ability to exploit new opportunities. Future volcanic islands will continue to emerge, particularly in the Pacific, where numerous submarine volcanoes approach the surface. These new lands will raise interesting questions about sovereignty, as nations claim territorial waters around volcanic islands that did not exist when maritime boundaries were established. Climate change intersects with volcanic hazards in complex ways that scientists are only beginning to understand. Melting glaciers on volcanic peaks remove the weight that helps contain magma chambers, potentially triggering eruptions as happened in Iceland following the last ice age. Changing precipitation patterns affect the stability of volcanic deposits, potentially mobilizing old ash and debris in devastating lahars. Rising temperatures allow human settlements to expand into higher elevations on volcanic slopes previously considered too cold for habitation. These interactions suggest that volcanic hazards will evolve in unexpected ways as Earth's climate continues to change. The development of early warning systems for volcanic eruptions continues to advance with new technologies and understanding. Machine learning algorithms trained on patterns from past eruptions can identify subtle precursors that human analysts might miss. Networks of cheap, expendable sensors could provide dense monitoring coverage of remote volcanoes. Satellite constellations offer near-continuous observation of volcanic activity worldwide. Social media mining captures real-time observations from people near volcanoes, providing ground truth for remote sensing. These advances promise improved volcanic forecasting, though the fundamental challenge of predicting complex natural systems remains. International cooperation on volcanic hazards has grown as recognition spreads that volcanic impacts transcend national boundaries. The International Airways Volcano Watch coordinates monitoring and warnings for aviation hazards. The World Organization of Volcano Observatories facilitates information sharing and capacity building. During major eruptions, international teams provide expertise and equipment to affected countries. This cooperation model, developed for volcanic hazards, provides templates for managing other transboundary risks in an interconnected world. The cultural evolution of humanity's relationship with volcanoes continues as scientific understanding displaces but does not entirely replace traditional beliefs. Many communities maintain dual frameworks, accepting scientific explanations while preserving spiritual relationships with volcanic landscapes. Modern media spreads both accurate information and misconceptions about volcanic hazards at unprecedented speed. Virtual reality allows people worldwide to experience volcanic eruptions safely, potentially building public understanding and support for hazard mitigation. The challenge lies in translating improved understanding into effective action when political and economic incentives often favor short-term gains over long-term safety. Volcanic resources will play expanding roles in humanity's future, particularly as societies transition toward sustainable economies. Geothermal energy from volcanic regions could provide clean baseload power for billions. Volcanic materials might enable carbon sequestration, with certain volcanic rocks capable of permanently binding atmospheric carbon dioxide. Rare elements concentrated by volcanic processes become increasingly valuable for renewable energy technologies and electronics. The same volcanic processes that pose hazards also create opportunities, maintaining the fundamental paradox that has characterized human-volcano relationships throughout history. The ethical dimensions of living with volcanic hazards grow more complex as our capabilities expand. Should wealthy nations help relocate populations from dangerous volcanic zones, or would this constitute cultural imperialism? How much should current generations sacrifice to prepare for volcanic catastrophes that might not occur for centuries? Who decides whether to attempt volcanic geoengineering, and who bears responsibility for unintended consequences? These questions lack easy answers but demand consideration as humanity's power to both create and respond to planetary scale changes increases. Education about volcanic hazards faces the challenge of maintaining awareness across generations when major eruptions might not occur within living memory. Traditional societies addressed this through oral histories and cultural practices that encoded hazard information. Modern societies must find equivalents that preserve and transmit knowledge about volcanic dangers across decades or centuries of quiescence. Virtual reality, gaming, and immersive storytelling offer new possibilities for making volcanic hazards real to generations that might never experience them directly. The goal is not to create fear, but to maintain respectful awareness of the forces that shape our planet. The philosophical implications of volcanism extend beyond practical hazard management to fundamental questions about humanity's place in nature. Volcanoes remind us that Earth remains a living, dynamic planet, indifferent to human plans and timescales. They demonstrate that changes we consider catastrophic are routine from a geological perspective. They show that forces far beyond human control ultimately determine the context within which civilizations rise and fall. This humility, enforced by occasional volcanic catastrophe, provides necessary perspective on human significance in Earth's long history. The search for life beyond Earth increasingly focuses on volcanic processes as potential creators and sustainers of habitable environments. If life exists elsewhere in our solar system, it might cluster around volcanic vents in the hidden oceans of icy moons. The chemical energy and thermal gradients provided by volcanism could support ecosystems independent of sunlight. Understanding how Earth's life relates to volcanic processes helps guide the search for life elsewhere. In this way, studying Earth's volcanoes contributes to answering one of humanity's most profound questions about our place in the universe. As we look toward the volcanic future, several certainties emerge from the uncertainties. Volcanoes will continue erupting as they have for billions of years, indifferent to human presence or preferences. Some eruptions will cause catastrophes that test the resilience of modern civilization. Others will provide resources and opportunities that benefit billions. Humanity will continue adapting to volcanic hazards through combinations of technology, social organization, and cultural evolution. The relationship between humans and volcanoes, begun when our ancestors first witnessed erupting mountains, will persist as long as our species endures on this volcanically active world. The story of volcanoes is ultimately the story of Earth itself, a narrative of creation and destruction, of terrifying power and life-giving fertility. From the first volcanic eruptions that built Earth's earliest crust to the future catastrophes that await our descendants, volcanoes have shaped and will continue to shape the stage upon which life's drama unfolds. They connect Earth's deep interior to its surface, link the solid planet to its fluid envelopes of water and air, and join our world to the cosmic processes that operate throughout the universe. In contemplating volcanoes, we confront forces that dwarf human power, while celebrating the resilience that allows life to flourish on this dangerous, dynamic, and endlessly fascinating planet. Understanding and respecting volcanic forces represents not merely practical necessity but a fundamental aspect of human wisdom. The mountains of fire that our ancestors worshipped as gods deserve reverence even in our scientific age, not as deities but as expressions of the planetary forces that created the world we inhabit. Every volcano that rises against the sky stands as a monument to Earth's continued vitality, a reminder that our planet lives and breathes through processes that began before life emerged and will continue long after humanity's chapter closes. In learning to live with volcanoes, we learn to live with Earth itself, accepting both the gifts and dangers that come from making our home on an active, evolving world where mountains can become clouds, seas can turn to stone, and the solid Earth itself flows like water given sufficient time and temperature.